Silo Solutions Private Limited. Sir is an editor for the IEEE Transactions on Smart Grid, IEEE Transactions Sustainable Energy, Current Science, and was an area editor for IET Generation, Transmission, and Distribution Journal. Sir has been granted fellowship from academics like NASI, INAE, and professional societies like IET, IETE, IE. Sir has also been recognized as an INAE Industry Academic Distinguished Professor. Sir's research expertise lies in the field of power systems, power quality studies, renewable energy, and smart grid. Sir, with this brief introduction, I would like to hand over the session for further proceedings. Thank you. Hello, sir. Hello, sir. Yes, sir. Sir joined.
Hi, good morning.
Good morning, sir.
Morning, sir.
Good morning. Good morning.
Good morning, sir.
Hello.
Yeah, good morning, sir. Good morning, sir. We can hear you, sir.
Yeah, so we can start the thing now.
Good morning, sir. Sir, can we have again a brief introduction, sir, about this, sir?
Yeah, should I start? I don't need introduction. I can start directly.
Okay, sir. Okay, sir.
So now you can start then. Actually, sir, we have given brief introduction already. So you can now share your screen, sir.
Are you able to see the screen now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So in the full screen mode, you are able to see.
Yes, sir. Yes, sir.
So some portion this is blocking.
Uh, uh, no, sir. We can see, sir.
You can see full screen, right?
Yeah, yes, yes, sir.
Okay. So the discussion will be today about the photovoltaic integration into the grid and basically the control challenges that will be coming while integrating it to the grid. Specifically, I have taken the photovoltaic as the renewable energy sources because in the Indian context, the photovoltaic is primarily a big renewable energy resource chunk. Though wind and other are also taking the lead, but photovoltaic will probably be ahead of them in the near future. And primarily, the difference between a photovoltaic based source and a conventional source is its physical property. That means a conventional source is a rotating machine and there is a big mass which is rotating and hence it has lot of kinetic energy stored in it. So the conventional source is a combination of power production along with a storage capability. So it is two in one. However, in case of solar photovoltaic system, it can produce power, but it cannot store by itself. Hence, there are a lot of challenges which need to be handled technically. Now coming to the storage, we all know that the photovoltaic based system requires a storage in isolated mode and in the grid connected mode it do not require any physical storage. But when I am telling physical storage, what I mean is generally a battery or in a bigger scale. It could be a pumped hydro or it could be even compressed air or it could be even gravity storage or in the newer trend you can go about hydrogen storage also. All these are physical storage. However, if we take the grid into account and we connect the solar system at one point and take the power output at another point, the grid infrastructure is just to wheel the power from one point to other, and that is a passive mode. However, in this case, the energy that is being inputted or the power that is being inputted at location A is consumed another location B and there is no really physical storage. But the source, that is photovoltaic source, will feel that there is a infinite storage which can accept any amount of power as well as can deliver any amount of power. So the grid, in a sense, acts like a storage of infinite capacity. But this infinite capacity discussion will go into a zero mode in a way, I will say, because of the increase in penetration of renewable energy sources. So as the penetration increases, this wheeling also will be challenging, and that creates technical issues, and we have to develop proper control strategy to handle those scenarios. With these basic preambles, if we see a grid connected schematic, will be having two converters. Are you able to see the mouse?
Yes, sir. Yes, sir.
Can I have some drawing pen also? Is there any pen? Yes. So you can see here that there are two sources. One is this source and another is this source. Now this is because there are two sources. That is two power electronic devices, not source. Source is the photovoltaic here. Therefore, it is called as double stage grid connected system. So in case of double stage, this PV is generally a low voltage case, and this low voltage case is increased its voltage here, and based on the availability of single phase or three phase, this DC voltage is decided. So the roughly we say that whatever is the peak value of your AC, so suppose let us take the single phase system. If it is 230 volt, then 230 into root 2 is the peak value, and the DC voltage should be at least more than this. So we roughly take a 1.5 factor or 1.8 factor and go for its calculation of DC voltage. So based on that, the DC voltage is decided, and the PV voltage based on its capacity and number of panels in series is decided. And that voltage here and the voltage here, here and here, there is a difference. Hence, we need this DC-DC converter. And generally, this DC-DC converter is a boost converter. However, since it requires two devices, people thought that can we go to a single device mode, and that is called as single stage grid connected photovoltaic system. Now let us understand little bit the control philosophy of this photovoltaic system. Now since there is a DC-AC conversion and one side is alternating and one side is constant, so we have to take a philosophy what type of controller we will use. Generally speaking, we can go for a PI controller, and that PI controller is suitable for a steps change sort of signal. So if your reference is like this, if it is at 10, suppose, and it goes to 15, so this type of state step change reference is quite suitable for a PI controller tracking. So generally in the DC side, we go for a PI controller. But on the contrary, when you go to the AC one, the AC side is basically a sine wave. So one approach is convert this sine wave to a DC and use a PI controller. Another approach is use this sine into the PR controller, that is proportionate resonant controller, and that scheme becomes a tracking control scheme. So in this, since there are two loops, One is for the DC voltage and another is for the AC side to act upon, because the inverter is just a passive device to pass the power from one side to the other. But the nature of these two sides are different. One is DC and another is AC. Therefore, we have to take two different type of control scheme if we are not converting the AC into a DC quantity. In three-phase scheme, we convert the AC to a DC by a DQ transformation. Now, if you look to the PR control here, we sense the current. Okay, so we sense the current here. Now, the current can be sensed by a Hall effect transducer sort of thing, or can be done by shunt, or can be done by any sophisticated way. Whatever it may be, if we sense the current, then that current is called as IG, that is the grid current. So at this point, the IG is a sine wave. It is a alternating wave. And based on the magnitude of the sensor, the scaling down magnitude of the sensor, you may require a gain to be added to the control loop. Now, this current, since is a sine wave, and this sine wave is to be little bit shifted based on our requirement, because we have to go for a power flow in the system. So we sense the voltage, and through a PLL we make a sine omega t form here. So the voltage signal is coming here. Voltage signal is coming here, and there is a IRAP going. So this IRAP is, let us assume, a number 10. So from this point, you are getting, a sine wave whose peak value is 1. Intentionally we have made it, whose peak value is 1, and the sine wave is exactly in phase with the voltage. And now you multiply it with 10. So the magnitude of this output here at this point becomes 10 sine omega t, where sine omega t is exactly following the voltage waveform. So at this point, the waveform is a same phase waveform with respect to the voltage. So if this is my voltage, then the control reference which is going will be like this, which is in same phase with the voltage. So since it is same phase with the voltage, and now I sense the current, and I try to go for a scheme using PR control, so that I will be able to make the error 0, then the current here becomes same as this output, and since this output is proportional to the voltage, hence the current also will be in phase with the voltage, and hence the operation of this whole photovoltaic system will be seen as a unity power factor operation to the grid point. Now here, the PR controller is generally a controller which is represented like K into S divided by S square plus omega naught square, S square plus omega naught square. This is because I am using a laptop, it is not coming properly. So omega naught square. And if we take the omega naught to be 314 in case of 50 Hertz system, then when the frequency is 314, so S is replaced by j omega, and when you make it square, it will be minus omega square. It will be minus omega square. And when the omega is 314, the denominator becomes 0 and the gain becomes infinite, and I will get the steady state error to be 0. That is the function of the PR control. And now, since there will be certain amount of current drawal in the capacitance path, which is nothing but your filter, but a filter can act as a load when it is in the fundamental form. So if that current is now added here, then the total current that is to be instructed for the PWM is now equal to the current of the grid, which is to be going, added with the current through the capacitor, and the overall current is now higher. Overall current is now higher. So that way we now go for its operation, and we derive the PR controller benefit, and the current group is introduced by this gain K. Now since you have the inverter, and that inverter simply pass the power from DC side to AC side, so you must maintain the DC bus voltage constant, because if we maintain the DC bus voltage constant, then this power balance automatically comes. Otherwise, if the input power is more than the output power, then the capacitor will discharge. Sorry, the capacitor will charge. Input power is more than the output power because excess power is there. And similarly, if the input power is less than the output power, the capacitor will discharge. Both the case we do not want, because it is not a storage capacity system. So whatever we want, that whatever power is coming, that power should go to the grid, and the grid will wheel the power to some other place. That concept can be implemented by making the DC bus voltage constant, and a PI controller can be used such that the magnitude of current reference can be now produced. Magnitude of current reference can be now produced. So this is the basic philosophy of any grid connected mode of operation. Grid connected mode of operation. Now coming to the single stage operation, as I have told, the philosophy will remain same. However, this DC-DC converter will be now removed, and the MPPT, the maximum power point tracking, which was the responsibility of this DC-DC converter in a two-stage grid connected mode of operation, is given to the inverter. So in this case, MPPT is for the DC-DC converter, and the DC bus voltage maintenance is for the inverter. But in a single stage operation, both the DC bus voltage maintenance as well as the MPPT is done by the inverter. So the reference voltage here, which is a constant quantity, becomes a variable quantity in the single stage operation. But by making that variation, we are able to remove one power electronic device, and hence it will be cheaper in some sense. However, the limitation is in the single stage is that this PV array should produce definitely certain magnitude of voltage which is around 1.5 times of the AC peak, and in case of three phase the peak is calculated from the line to line voltage, and hence the voltage requirement from the PV array is large, and hence to get that large amount of voltage or big amount of voltage we need many PV panels to be connected in series. So, a single stage system requires higher capacity operation. On the contrary, a two-stage system can be used for low power as well. Now, generally speaking, when you have a grid connected operation and that grid connected operation comes from a rooftop photovoltaic system, then it is a little bit low power capacity, and hence we can use a boost converter and then an inverter, and it will be connected to your main point, main switch point, or maybe at a specific three-phase point if it is three-phase load, or if it is single phase, it can be connected to a single phase point. Now, when you connect that, that load of the house is also connected to that point. Hence, your PV array is in parallel operation with your load as well as grid, and the balancing of power happens automatically. The power goes from the grid to the load, or the power comes from the PV to the grid based on what is more. If the load is more than the PV, then the grid supplies the excess amount. If the load is less than the PV output, then the differential amount goes to the grid. So this becomes a grid interactive hybrid operation. So when we go for the grid connected operation, as I have mentioned, the PLL makes a big contribution. The voltage waveform need to be in known a priori, and this is to be known based on the PLL, and we cannot say that it is just 230 sine omega t, where omega is 314, because that is nominal value, but in real sense it does not remain at 230, as well as my frequency is not 50 hertz. Because of that, the voltage waveform need to be sensed, and PLL is one of the way to sense the signal. There are some other way also that is called as uh, unit template approach, where the waveform is directly sensed by the sensors, and the unit template is calculated based on the peak. So there are two things here. In the PLL, we sense the omega t portion, that is, and we calculate sine omega t and make forcibly the gain to be 1. So it becomes a unity peak sine waveform, which is analogous to the voltage. On the other hand, in case of the unit template based approach, we sense the voltage and try to estimate the peak of the voltage, and we divide the waveform with the peak. So in one sense, we sense the frequency using the PLL. In another sense, we sense the magnitude or estimate the magnitude. If we take both to be an estimator, PLL estimates the frequency, and the unit template approach estimates the peak. But in both the case, the output is a sine wave of unit amplitude, and based on its approach of estimation of the quantity, which is difficult and more erroneous, the result will be different. So since it is an estimation and that estimation will not be absolutely correct, therefore there will be a dynamics involved. For example, if the frequency changes, there will be a dynamics in the PLL section, and if the amplitude changes, also there could be a dynamics coming in the PLL because of the transient in the amplitude. Similarly, in the unit temperate based approach also, when there is a change in the amplitude, there will be a transient, and that transient need to be properly seen. So both the two will be having their own influence in the dynamic sense, and when the dynamics are going on, in that case, this need to be properly taken care of. Otherwise, the system may become unstable. Now, since my IV curve exists, and corresponding to that IV curve, I can make a PV curve, and there will be a MPPT point. And that MPPT point is actually tracked by my converter, and the MPPT can be now or the inverter can be operated at up MPPT point, and that is called as flexible MPPT, derated mode of operation, up MPPT. So many names are there. So based on the requirement, instead of operating at the peak, we may operate at some other point so that we can have a resolved margin like our conventional synchronous machine. So this is called as derated or op MPPT or flexible MPPT operation in the power sector. So the photovoltaic control can be now done, and the photovoltaic system, which was thought to be a uncontrollable system in the range in the perspective of power, because the radiation or illumination cannot be controlled, but now it can be a dispatchable source in a limited sense, at a specific operating point, if we derate the power of the photovoltaic system. Similarly, since you have an inverter, the reactive power can be produced from the inverter, and it becomes automatically a controllable reactive power source. So based on that, if we go for a real power control scheme, the DC voltage reference need to be properly defined to take care of the derating and the real part component. That means this will be used by the voltage multiplied by the voltage waveform to produce the real part of the sine wave, and the voltage is sensed, and a voltage reference control is defined to produce the quadrature component of the current with respect to the voltage waveform. So one is corresponding to the voltage, in phase with the voltage, and another is 90° to the voltage. That means this corresponds to the real power and this corresponds to the reactive power. And now, if this DC voltage reference is properly defined, instead of MPPT, if we do this as my DC voltage, this as my DC voltage, then automatically I will operate at a derated mode of operation for the solar photovoltaic system. So that says that both real and reactive power can be controlled, and proper design of PI or PR controller need to be included in the solar photovoltaic grid connected mode of operation. So as we now start pushing power into the grid, both real and reactive power is pushed to the grid, then the voltage control and frequency control or frequency response control can be done with respect to the grid. So if we do that control, then we'll be able to handle the intermittency and we can go for the ancillary services from the solar photovoltaic systems. Now, there are certain interesting issues that may come in the photovoltaic operation. So when you go for a no photovoltaic scenario, suppose this is our load core, there is no photovoltaic. Now, as you increase the photovoltaic penetration, gradually, the power goes on reducing. The power goes on reducing at noon point, and beyond certain value, you can see that it goes to the negative value. It goes to the negative points. So that means there is a reverse power happening. So if you have a distribution transformer and to the distribution transformer there is a feeder and you inject photovoltaic power, as long as the load is able to consume that power, the net power will not cross the transformer. But when the photovoltaic injection is more than the load, it will cross the transformer. And when this reverse power flow occur, the the system is not designed for that. Hence, we should not go for a reverse power flow in the operation. Otherwise, you have to take care of the protection and other issues in a big way. Now, similar phenomena may happen while you will be going for a photovoltaic injection into the distribution system. When the distribution system is radial and you try to have photovoltaic at the end point, then there will be power flow here, and that power flow will basically increase the voltage at this point because the current can move from higher to the lower one. Lead. So if this voltage is higher, then only you will be able to have a power flow from this photovoltaic towards the other point. And that will now increase the voltage at different points in the feeder, and that increase in voltage may kill your loads, and this voltage rise phenomenon need to be curtailed. A lot of research need to be done in this aspect. Similarly, a further interesting issue occurs where the loss in the distribution network increases because of the solar photovoltaic injection. You can see here, if this is the normal loss scenario, now as the penetration increases, there will be a reduction in the loss, obviously, because the net current in the feeder will reduce. But beyond a point, when the solar power becomes more than the load, then it will start pushing the power in the reverse direction, and again the current starts increasing. And it may so happen that at a higher penetration level, the loss may be very high, normal to that of the load loss scenario. That means if the load is 100 kilowatt and if you if you try to push the solar photovoltaic of 300 kilowatt, then this extra 200 kilowatt is much more than that of the load, and hence your loss in the system will increase, and that loss increase need to be handled by the infrastructure of this distribution network, and that infrastructure increase will now put lot of cost burden on the distribution system. Hence, the the infrastructure revamping may be required, which is a big challenging task. Hence, we have to go for a proper power management of the solar photovoltaic system, maybe by making derated operation or putting storage in parallel with the photovoltaic system. Storage in parallel is a very costly device as compared to the derated mode of operation as on today. So this issue of inertia can also play a very vital role in case of the photovoltaic system. As I have already told you, the rotating machine is having a half I omega square stored in it, and that half I omega square is released whenever there is a need by the load, and that is called as inertial power. And in case of solar photovoltaic system, since we do not have that inertial capability, we have to artificially using control provide this inertia, and this inertia is called as virtual inertia of the solar photovoltaic system, or synthetic inertia, artificial inertia. Lot of names are there for this inertia, and to get that inertia we must operate the photovoltaic into a derated mode of operation, or MPPT mode of operation, or um, flexible MPPT mode of operation, and this derated solar photovoltaic system need to be instructed with respect to a quantity called your control quantity derived from the frequency of this uh, grid, and hence the real power can be now increased or decreased based on the delta M. And similarly, the power quality issue can also be a problem in case of grid connected solar photovoltaic system, because the grid is a having sinusoidal voltage, but the current injection can be now non-sinusoidal, and that may create power quality issue. Thank you for giving me a patient hearing, and all these what I discussed can be put into as a control problem, and different controller can be developed. Even we can go for intelligent control or artificial intelligence based approach for giving real control of performance. Any question? You can take something, otherwise you have to close the class. Are you able to hear me?
Yes, sir. Yes, sir.
Ah. Any question is?
Yes.
Sir,
Participants, any questions? Yeah. Yes.
sir, thank you for your session, sir. I have one query, sir.
Yeah.
Suppose if the estimated unit template is not pure sine wave with one peak of 1, so then how to change it, sir? If it is not pure sine wave, I think the harmonics will inject. No, sir. So then
See,
how to proceed?
that is
How to
why,
clean that?
yeah, that is why I told you there are two approach. One is you take your distorted waveform, pass it through a PLL. Then the PLL output will be your omega t, and you make sine omega t by yourself. Okay. So even if your waveform is distorted, your unit template produced by the PLL is not distorted. So your current injected into the grid is not distorted. Am I clear now? One point.
Yes, sir.
Yes or no?
With PLL, yeah, yes, sir, yes, sir. With PLL, okay, sir. With the unit template, I am having doubt.
Okay. So this is also a unit template because the output is a unity waveform sine wave. Okay. Now, if we directly sense these waveforms, sample by sample, and you estimate the peak and you divide, then your waveform will be distorted, and the current waveform also will follow that distorted one, provided your PWM is perfect. So in that case, agreed, current will not be a sine wave. So you have to pre-process the distorted waveform of the voltage, and then you have to take the sample. So sometimes, therefore, we go for a a what I will say filter, and in the single phase we go for that filter operation initially and make the sine wave perfect in the initial beginning point. For a three-phase system, what we do, we use this to a DQ transformation, and we use the filter in the DQ part. However, all these things are of academic interest to some extent. Reason being, the voltage waveform does not distort in a big way in a grid operation. The distortion what occurs is in the current, not in the voltage. Therefore, this theoretical interest that the voltage will be distorted by a large magnitude is basically an assumption, not a real case scenario. Am I clear?
Yeah, yeah, it's clear, sir. So, like you said, pre-processing with some filter means how to select or design such filters. I mean, which kind of filter we have to choose, sir, for pre-processing?
Mostly you can go for your simply a low pass filter sort of thing, but you have to see the time constant and how much delay it is introducing and what is the distortion that is coming, how much high frequency distortion you are having in the waveform. Otherwise also there are many other techniques to remove this and make it a sine wave. Many signal processing techniques are there. You can go for even SBD, you can go for some intelligent technique, you can go for Kalman filter, many things are there.
Okay, sir. Thank you.
Okay. Any other thing? I can take any one more question if it is there, otherwise I have to close it. Okay, if no more question.
Sir. Yes, sir. One more question from me again, sir. Sir, like you mentioned, we have to go for towards intelligent controllers. So, can you please mention few of them so that I can go through in
You can
literature?
go for neural network because all these are pattern recognition approach. So you can go for some sort of neural network approach. Or if you are going for KPKI tuning, you can go for some fuzzy control. You can go for some hybrid PI control. Okay.
Okay, okay, sir. Thank you.
Okay, so we can conclude the class.
Yes, sir. Thank you, sir, for giving an opportunity to learn from you. Thank you for sparing time for us in spite of a busy schedule, sir. Thank you so much, sir.
Thank you. Okay.
Hello.
Yes, sir.
Neil.
Yes, sir.
So dear participants, we will meet again then 12:45.
12:45, sir. Mr. Sukanta, sir, will be
Dr. Sukanto, not Miss
Dr. Sukanta, sir. Yes.
He will be there. We are sorry for that. Unfortunately, that our sir, Misra sir, has some urgent work. So he told me suddenly that he can continue only for 1 hour. So we could not arrange for rest of the time. So we will meet again then 12:45. Okay, please be with us. And tomorrow there is a test at last session. Okay, this test will be the mandatory test for all the participants. Otherwise, we could not provide you certificate. Please, those who have registered, please be with us at the last session. You have to give the test. That is the mandatory actually, as per ATAL rules and regulation. Okay. Thank you.
Sir, can we have all these sessions PPTs at the end of FDP?
Actually, we are recording all the program, right? So we
Yes.
will upload in YouTube also. So in the name of this FDP, if you search, then you will automatically get all the PPT. PPT means your recorded lecture. Okay.
Sir. I
Actually,
am asking
some
about
experts
PPT.
are not ready to provide their ready-made PPT because of some issues. So we are not asking them to provide. Okay, some are giving, but so actually we are since we are recording, so whole class or whole lecture will be there with us. So no need. I think no need to no need for that PPT.
If possible, try to share
Okay,
some
okay,
PPT
100%. From
provide.
our side, we will try.
Yes.
Okay,
Okay,
and
sir.
we will provide you YouTube link also
Okay, sir. Thank
to
you.
your email.
भैया अमूल का वो इनर दिखाइएगा ना जेंट्स वाला
क्या साइज होगा?
85 जो पीछे वाला पिछले दिन ले गए थे ना वो वही वाला
Good afternoon, sir.
Hello.
Yes, sir.
I think sir has already joined. Okay.
Okay, sir.
Professor Sukanto.
Yes, Dr. Sarkar, how are you?
We are we can proceed now.
Yes, we can
Okay.
proceed.
Anil, please introduce.
Okay, sir. Good afternoon, sir. Welcome to the FDP program on recent trends of control systems in power electronic converters. It's my pleasure to introduce about Dr. Sukanta Haldar, sir. Sir is assistant professor at Sardar Vallabhbhai National Institute of Technology, Surat. He received his MTech and PhD in electrical engineering from IIT Roorkee. After PhD, he joined Rolls-Royce NTU Corporate Lab, Nanyang Technological University, Singapore as postdoctoral fellow. He worked for nearly 2 years for Rolls-Royce in Nanyang Technology University, which is holding QS World Ranking 4th in electrical engineering. Later, for his second postdoctoral in 2019, he moved to Charge Lab, University of Windsor, Ontario, Canada, which is the biggest EV lab in North America under Tier 1 Canada Research Chair, professor in electrified vehicles. He was responsible for developing wide bandgap based inverter for EV and was involved in developing intelligent control for EV in collaboration with Magna International and Concordia University. He works broadly on next generation inverter development, intelligent EDTS for EV application. His research interest includes WBG, wide bandgap inverter development, gate driver design, electric vehicle, PMSM drives, multi-level inverters, machine learning based motor control, sensorless drives. With this brief introduction, I would like to hand over the session to sir for further proceedings.
Thank you, Anil, for your nice introductions.
Thank you, sir.
Okay. So, good afternoon, all. I welcome you in my presentation. So, let me share my screen. Am I audible to you?
Yes, sir.
Okay, good. So, Anil, can you please confirm whether my screen is visible?
Yes, sir. It's visible.
Make it presentation mode. It will be better, I think.
Yes. Okay. Hello.
Yes, sir.
Am I audible? And just please let me know whether my screen is completely visible.
Yes, sir, you're audible. Screen is also visible. Just means need to make full screen. Yeah, now it's okay, sir.
Power electronics and intelligent control for EV application. Okay, so rightly said by Tata Motors company. So they are saying that, okay, goodbye fuel, hello electric. So this means they are trying to welcome electric. So electric in terms of electric vehicles. Okay, we are actually nowadays everywhere we can see the research is ongoing on electric vehicle side. So why we want electric vehicle research and what are the updated technology with the industry? So those part we'll try to understand in today's sessions. So let's try to have a brainstorming sessions. And please feel free to interact during the sessions. Okay, it will be I'll try to make it more attractive. So as you know, the whole world is suffering from COVID. Okay, so and now our concern is COVID. Okay, so and day by day, a different kind of virus is also coming. Previously we suffered from Delta, now it's coming as Omicron. Okay, so we have to be careful about that. Now the point is let's start from the very big source of the point. Okay, so where we are lagging, so whether we are good enough to protect everything, whether we are doing our duty, whether we are responsible uh, in terms of like most of you are engineers, okay, from the engineering background. So as engineers, what is our duty for that? Okay, whether we can predict, okay, whether we can prevent, whether we can give our a better society, whether our healthier society, right? So this was predicted initially, predicted in terms of if you recall, say in few movies. The director has shown, okay, this kind of situation may happen, but we are not aware of that. Okay, now again we are having a challenges of the carbon. Some of the movies showing, okay, one time there will be a time so when the earth will be full of carbon. So full of carbon means we have to suffer for the oxygens. Okay, so we have to get our own cylinder, and it's very difficult. Wearing a mask, it's quite a difficult for us. So everyone has seen in our these pandemic situations, but can you imagine how it will be difficult to wear a cylinder, so holding a cylinder and taking oxygen from there? Okay, so this is our concern. So we have to be responsible, and we have to respond from our side as engineers. What we can do, so we can give a better or healthier world, right? So we want to give a technology which is environment friendly. Okay, so we cannot consider all the things, but as engineers we can give. So like if you go for the electrical vehicle technology, so as we know, so this is actually emission free, zero emission technology. So as a researchers in the field of electrical vehicles, so what we will try to do, we'll try to develop, or we'll try to put our more effort in these directions of the research, so that we can provide a better society for a better living, right? So in view of that, so we'll try our introductions. Okay, so this will be our this will be the content of the presentation, a brief overview. Okay, so first of all, why we need electric vehicle, then what are the different performance target set by different industry, okay, or different energy agency. Then we'll try to understand who are the pioneer in the power electronics and drives industry. So what their demand, okay, what is their target they want to achieve in coming years, okay. Then we'll try to understand industrial case study and research opportunity. So as an academician, so what we need, so we need to get the problem from the industry. So industry is providing solutions, okay, in collaborations with the academic. So academic and industry collaborations, research how it works. Okay, so that what are the research opportunity we'll discuss. Then we'll go for the research in next generations inverter. So like in next generation inverter, we have a WBG inverters. So in WBG inverters, what are the research ongoing? That part we'll discuss. And after that, we'll try to learn the machine learning based intelligence electric drive track for traction system. Okay, so that part is very important because nowadays all we know that machine learning is the next electricity, so which is going to change the world. So in that part, we'll try to understand how we are actually contributing in the electric vehicle domain. Okay, and after that, what are the skills and tools we need to develop? So that part also we'll discuss in our session, right? Am I audible? Just in between, please let me know. Otherwise, nowadays, due to COVID, you know, we are in online mode. Sometimes the connections is not there, and I am discussing here. It will be difficult. So in between, I'll ask. So just please try to respond. Whether am I audible?
Yes, sir. Yes, sir.
Good. Thank you. Thank you so much. So let's try to introduce electric vehicle, right? So already we know. So just to recap, so electric vehicles, what electric vehicle actually doing? Electric vehicle actually creating a revolutions in automotive industry and transportation system, because the electric vehicle we are claiming as zero emissions, right? So and high power density and high efficiency of ETDS, electric traction drive system, are utmost need, right? So efficient. So when we are talking about electric vehicles, so how electric vehicle works, we'll see. And we want a inverter or converters where the power density is high and also efficiency is high. So our concern will be how to improve the efficiency, okay, in ETDS, electric traction drive system. So that is the utmost need. Okay, so and next, what we want to do, we want to extend the driving range. So for example, so you are starting from Kolkata and you want to go to Siliguri, right? So you have a quite big distance. So you want to cover in short period of time. So if you have electric vehicle, and how we can get the higher speed operation. So extended driving range. So how we can get, so in terms of battery capacity or in terms of control. Okay, so how we can extend our driving range. Okay, so in enhanced e-drive system, so this is also a bottleneck. So research is ongoing in these directions. Okay, so if you see if we just quickly do our literature survey, then we can find that okay, high frequency inverter actually promises the solutions to achieve fastest speed range. So how we can achieve the fastest speed range? Using our high frequency inverter, right? And in efficient ETDS system, so generally in terms of motor, when we talk about motor, so that part we'll discuss what are the different component of electric vehicle. There we'll see how this IPMSM is contributing their part. So IPMSM is taking a vital role in ETDS system. So interior permanent magnet synchronous motor. So due to its several advantages features, so already we know those who are working in this area, they know okay why IPMSM is suitable, because it's compact size, okay, and high reluctance torque productions, okay, and as compared to other motor, and efficiency, robustness, those are the advantages features we can say. Now efficient control of ETD systems play a vital role in its performance and reliability over time. So efficient control systems, so in that part we'll try to understand so how our machine learning technology is contributing, or they are trying to take a vital role in performance and reliability over time. So in future, so what is the next generation technology that we will try to understand, say, in this session. Now, what is our motivation? So when you are working in particular field, so you have to motivate it first. Okay, so self motivations is very important, and interest must be there. So what is our motivations behind that? Okay, we are going to contribute something. So what we are going to contribute? So we are aiming to contribute the government of India emissions So India is targeting for electric vehicle. Okay, so they are trying to achieve some range, you can say, okay, so by 2040 we'll be having this many number of electric vehicle, or we want to uh, completely remove other vehicle and will completely use electric vehicle. So government of India mission electric vehicle is ongoing. If you go for the NITI government websites, there you will find, okay, so there are a lot of government policies coming, okay, for our to promote our electric vehicles research, okay, and our government agency also giving funding for this research. So what we are trying to do, we are aiming to contribute the government of India mission electrified vehicle by providing an efficient and intelligent ET drive system, so electrical traction drive system for electric vehicle application, right? And also we are trying to contribute a productive, value added in an effective and sustainable use of research results to the industry. So research industry is also dependent on us. Okay, we are doing research, and this research, so that value added research or productive research results, they are going to incorporate in their production, right? So this is also a huge impact. So if you can provide this, you can contribute in that directions. And what we are also doing, we are actually doing technological advancements towards building the intelligence ET drives, ETDS for electric vehicle application. So technological advancement, right? So now we are transforming from uh, fuel-based drive fuel-based vehicle system to our EV system. So technological advancement, how we can adopt those technology, how we can educate ourselves to uh, familiarize with those technologies. So that part also will be improved in this research. And the transfer of knowledge to the industry and continued advancement in power converter technology will be a paradigm shift in ETDS design and development. Okay, and by this research, what we are trying to do, we are trying to create a platform of collaborations, bringing academia and industry together to create innovative and promising solutions for future electric motor drives technology in India, right? So that part we'll try to discuss. So this is our motivation. So first, why we are doing this research, we have to know, okay, how we can contribute to our society, to our country, and overall how we can contribute to the world. Okay, so this is our motivation. Now what are the different performance targets set by different agency? Now this data actually is taken from Department of Energy, USA. Okay, so if we go through their website, you will find, so what they are trying to do, so this is a performance target. So performance targets, they are trying to achieve a peak power 200 kilowatt, okay, so and continuous power of 110 kilowatt. So voltage rating, what will be the voltage rating up to 1200 volts? Switching frequency, they are trying to get 30 to 50 kilohertz switching frequency. That's why we'll see how in WBG research we can through WBG research we can achieve those targets. So these are the performance targets set by Department of Energy. Okay, and maximum current in terms of torque. Okay, so if you say torque ripple, so we want to minimize the torque ripple, so torque ripples must be below 5%. So we're trying to get this. And inverter technology, so they are trying to set the performance target in terms of inverter technology, and they are going to use WBG based device, so wide band gap device in terms of silicon carbide or gallium nitride. And machine technology, if you consider machine technology, non rare materials and cooling technology, that is very important. So now when we talk about inverter, so or motor, so cooling technology also important. Most of the electric vehicle applications, okay, so the inverters which we are going to use, so that must be a liquid cooled inverter. In liquid cooled inverter, generally we used water and glycol. So here what they are trying to do by 2025 R&D target. So power electronics, the cost per kilowatt must be $2.7, and power density what they are trying to achieve, so 100 kilowatt per liter. And electric motors, in terms of electric motors, is a 3.3 dollar per kilowatt, and power density 50 kilowatt per liter in terms of motor uh, power density, right? So, and honestly speaking, we are good as an Indian, so we are good in power electronics research or drives research, but we are lagging in the directions of motor design. So all the motors we are getting, so this part China is leading, so we need a good engineers. Some of you can actually contribute by designing a suitable motor for our electric vehicle. Okay, so you can also focus in this direction for your research. So design of electric motor, right? So now let's try to understand the power electronics target. So what is the power electronics target? So power electronics target, so this diagram actually is showing if you are going to design inverter, so what will be the cost? Okay, different cost. So here you can see that gate driver, in terms gate driver is actually 24%, okay, and control board 16%, and capacitor also DC bus capacitor 12%, power module is actually taking 23% of the total cost. So if you compare, so you can see that power module and gate driver is taking a larger amount of cost, right? So if you want to develop your own inverter, so this will be the cost breakdown. Now in power electronics inverter component, if you see here cost, we are trying to achieve $2.7 per kilowatt. So this is this data is taken from one industry. Okay, so there a power modules is cost is $59. So these are the different cost. I more interested about the total cost. Total cost is $270 here. Now need of the hour, so what is the research we have to do here? So we need to improve our gate driver performance, right? So how we can actually improve our gate driver performance, we'll see in our coming slides. Okay, now better power modules, whether we are good enough to provide a better power module, so how we can modify it or upgrade our design, so that part also need to be careful. Now here if you talk about inverter, there we have our capacitor, so and how we can improve our busbar design. And also one of the challenges optimizing the capacitor design, so this involves actually the cost also, right? So if you can optimize your capacitor design, so then you can actually minimize some cost. And also some research is going on to reduce the computational cost. So there how we can contribute through our control algorithm, so that we can reduce the computation cost. Okay, so so that we can meet our cost target. So this is our power electronics space target. So if you want to design one inverter, clear? Oh, am I audible?
Yes, sir.
Okay, good, thank you. And please let me know, my screen also changing?
Yes, sir. Yes, it's changing.
Okay, good, thank you. Now, if you talk about growth path in global EV market, so there you can find that, okay, India, so I have highlighted India. So by 2025, 2030, so 2040, so this is the future projection. So here you can see so actually the market demand and the productions also will be high in India in future. So okay, So this is the data taken from Mahindra Electric. So for your reference, you can actually follow Mahindra Electric guidelines. Okay, now here the growth in China, if you see growth in China, so here already largest EV market by volume. If you consider, already they have set a largest EV market. Okay, so they have massive vehicle route through subsidy, and this policy they are called this policy is calling as government led, people supported. Okay, and growth in Norway, if you consider the largest EV market by market share, so they are having a largest market share, and premium vehicle route through mix of incentive and fees. So this is also government led and people supported. Now growth in USA, so this is a premium vehicle route, so this is people led and government supported. Now EV growth in India, if you consider, so massive vehicle route, so we are having a massive vehicle route. This is the opportunity to EV researcher, right? So a massive vehicle route we are having with improving the total cost of operations of EV. So we actually government led and people supported. So this is the global growth rate, right, or growth path in the EV market. Okay, you can see. Now, as an Indian, so we'll first concentrate on Indian market. So India, a unique market, right? So we are dependent on three-wheelers, we are dependent on two-wheelers. As compared to four-wheelers, mostly we can see that we mostly dependent on three-wheelers or two-wheelers in India. So, and if we consider that India is one of the largest markets in the world in terms of three-wheelers. Okay, so largest market in the world in three-wheelers. So electric vehicle researchers can focus how we can actually overcome the drawbacks. Okay, and we can provide a better solutions for three-wheelers and complete electric vehicle in three-wheeler case, right? So in two-wheeler also we are actually moving forward. Okay, you can say that in 20 millions in year 19, so here 0.7 million sales in the year of 2019. Okay, and also in commercial sectors, if you see overall good transportations and personal in terms of personal car also, so EV market is growing. Okay, so we have to focus how we can actually provide a better solutions. Okay, now as a EV researcher, so we have to find who are the pioneer in power electronics and EV industries. So how many of you heard all the names? I think all of you know, because you are if you are working in this area, so you might have know. Okay, so power electronics field, already we know Semicon, so they are the pioneer. Okay, so and Infineon also is contributing a lot in power electronics domain. Then we can actually see the Cree GAN system, then Magna International, ABB, Eaton, all are the pioneers in power electronics domains, and many more. And we have EV manufacturers. In terms of EV manufacturers, we have Tesla, Tata Motors, Ford, Mahindra Electric, then we have a BMW, then we have a General Motors, and also we have Nissan Leaf, right? So these are few data, and the EV researcher must follow what is the update ongoing in terms of power electronics research. So you have to follow this website, or you have to follow this industrial outcome, or what they are looking for in terms of EV manufacturers. Always will look for Mahindra Electric or Tesla or Ford. What is their demand? What research they want from us as an academician, so we want to contribute. Now let's talk about our technical term. So if you just want to give a simplified structure of electric vehicle. So you can see that this is our vehicle and it has different parts. So we have a charger, we have a battery, then we have a converter, then after that we have an inverter, and then here it is motor. So motor is actually driving our wheel, and here is converter and other accessories. So mainly here today we'll discuss about this part, inverter and motor part, right? So inverter and motor part today we'll try to understand, and how we can control the motors as well in using our machine learning technology. Now let's try to understand one EV structure. So Tata Motors Gyptron. So how many of know Gyptron technology? Anyone? Have you heard? Yes or no? Okay, fine. So actually Tata Motors is providing Gyptron technology. So they are actually combining all these inverter, motor and their battery pack, and they're saying calling this is a Gyptron technology, and this battery base also is coming with the Gyptron technology, and this is incorporated in a Nexon EV. So Nexon is one of the model from Tata Motors. Okay, now here what they're doing, so they're actually using permanent magnets gross motor to drive the wheel, right? So here they are also using battery and inverter. So inverter, they have used here water cooled power electronics architectures. Okay, so we are not going in details what is the inside the battery, what is inside their inverter technology. So just to give an overview, so this is a Tata Motors Gyptron technology, and they are actually quite good. They are actually is having over 1 million kilometer of testing experience in terms of battery. Okay, now coming to our interest part, why power electronics? Okay, in electric vehicle research. So power electronics, we'll see how power electronics is contributing a lot in electric vehicle domain. So five power electronics in broad, when we try to understand, so we'll see that, okay, power electronics we generally use for power conversion and electric drive system. Okay, and power conversion, here you can see one diagram. So this is one of the semicron inverter. Okay, so in case of power conversions we used, and electric drive system, so this is one Danfoss drives, so we are showing you. And electric vehicle, in electric vehicle here one, this one is a Tesla model. Okay, so Tesla is pioneers in electric vehicle. So power electronics are contributing a lot, and here along with our car, so here some of the industries are looking for efficient power electronics, or you can say next generation power electronics. So here you can see that Rolls-Royce, so they are actually targeting to shift their aircraft to completely electric driven. Okay, so electric aircraft, they are trying to achieve electric aircraft, and some of the news also you might have seen, so they already achieved this part, so complete electric aircraft. Okay, so and also people are looking to contribute in marine also, so using our power electronics. Now coming to this interesting part, so we know that power electronics. Okay, now how we'll transform this power electronics to next generation power electronics? So what is the contribution, so where we can contribute? So power electronics, people are looking for more reliable power electronics. So in terms of reliability, which one is good? So there will be reliable power electronics. Then after that, what we are trying to do, we are trying to make it compact. So once you are making it compact in size, so this also will give you added features. Okay, mainly most of the company is looking for this point, compact size. So electric vehicle, you have a size constraint. So we are trying to contribute here so that our inverter can fit into our desired size specifications, right? So for example, if you compare with normal IGBT based inverter with your silicon or gallium nitride based inverter, you will see that huge reductions in size. So you can actually save the size by using WBG inverter. So compact size. So this is one of the constraint. Then what we are doing, we are actually trying to improve the efficiency. So how we can improve the efficiency, how will improve the efficiency? So this is a simple concept. We are trying to minimize the loss. So how we can minimize the loss in power electronic circuit, then we can improve a more efficient. Then obviously cost is the one important factor. So whenever you are going for electric vehicle, you want to purchase an electric vehicle, cost is also a challenge. So you have to provide a solutions where cost is important. So you have to minimize the cost, production cost, and then through by this process, reliable, compact size, efficient, and cost effective, then you can actually make a power electronics suitable for our next generation technology. So that's why we are calling it as a next generation power electronics. So in next generation power electronics, what are the changes we are going to make? So those things we will try to understand, and what are the research gap we have, so that part also we'll see in coming slides. So just please acknowledge I'm audible and screen is visible.
Yes, sir. Yes, sir.
Okay, good. Thank you. So this is one industrial inverter. Okay, so this is having some proprietary informations. Okay, so I have already given the citations from them, reference. So this is one of the Ford inverter I am showing you. So how this is actually taken from one car, and I'm showing you. So this kind of compact structures that they are showing. So here they have used IGBT, so the size was more, so we have to minimize those size. So this is Ford inverter, this is the gate driving board. So you can see how big it is, and the inverter also, it is big. Okay, so and power module, so inside the car, so the power modules is looking like this, and these are the sensor boards. Okay, so here you can see some of the bullet points. So heat sink design also a challenging job. So few researchers also working in heat sink design. So this technology is actually having a liquid cool. Here you can see in Ford inverter series just input output. So through that we are actually giving we are passing a liquid in terms of water and glycol. So coolant, what type of coolant we are actually using? Water and glycol. And in terms of flow rate, so this is 4 to 20 liter per minute. Okay, so we'll show you how the cooling system or cooling arrangement is done in EV research lab. Okay, for the testing purpose. So that part also will show you in coming slides. So the microcontroller, what they have used a TI microcontroller. So mainly TI's C2000 series microcontroller. So you can use for this kind of inverter technology. So EV inverters with the industry available. So I'm showing, and this is one of the inverters they have with them. So internal structures, if you just open your electric vehicle, so you'll find this is your internal structures. We have a motor, front motors with inverters, and we have rear motors with the inverters. So and the battery pack are placed like this. Okay. So we have 400 volt DC bus systems and also 800 volt DC bus systems in some of the varieties like Ford Focus and Porsche Taycan. So they are having this structure. So this is the main battery pack. Okay, now this part we will not discuss. So how we can do the charging, discharging. Okay, so and research on battery. So maybe some of the speaker already has discussed battery research, or hopefully in upcoming sessions also regarding the charging, we will have some overview. So motors, what kind of motors actually they're using? Motors, they're using actually permanent magnetic synchronous motors or induction motors, especially in Tesla is using induction motor. Okay. So inverters, either you can go for silicon carbide or IGBT based, or you can go for gallium nitride. Now, so if you just try to understand the E-drive, so this is the state of art of the E-drive. So E-drives, what we have a motor, then we have inverters. So just we are trying to minimize so that we can clearly understand. So other part we have like a battery systems or battery charging systems. We are trying to eliminate for now. So we'll focus on just what are the 5 PMSM. Then we'll focus on this WBG inverter. So this is the designed inverter. So you can see here how compact is this inverter. Okay, so this inverter actually you can take in your palm. Okay, so you can hold in your hand. So this is a very small inverter, so with high power density. So 5 PMSM already you know that it is having a high power density, high torque to inertia, then high efficiency over wide range of torque and speed. Okay, and reliability also. Okay, so that's why we are going for PMSM. So this is one of the PMSM designed in my previous lab where I was working. So this is the designed PMSM. So in that lab, what we used to do, so we designed in ANSYS, then we used to uh, uh, give for the production. So we designed our own motor and produce, and that is for the industry. Then in WBG inverters research, what we are doing here, so we are trying to minimize the size, and we are actually here this design was targeted to fix this inverter in-house with the motor, so with the motor housing. So we can fix this inverter in motor housing itself, so you can save a lot of space in your electric vehicle. So why WBG inverter? So it is having a low switching loss, high operating voltage, high switching frequency, high temperature operation, and improved efficiency. Okay, so this is a brief overview. Okay, so this is one ETDS systems. In ETDS systems, we have a motor and we have an inverter, and control part later stage we'll discuss. So clear this point? Hope this is clear. Am I audible?
Yes, sir. Yes, sir.
Okay, good. Thank you. Now we have IGBT based motor drives. So we have some challenges and opportunity. Okay, so lower switching frequency. If what is the challenges in IGBT? If you see, so IGBT, a lot of research already has been done, and few research still is going on. So, but we are suffering in terms of switching frequency. It is having a lower switching frequency operation. So, below 15 kilovolts is preferred, and how is higher switching losses in the module. Okay, and in terms of size, it is also is having a required a huge size, so bulky. So and DC capacitor size also more, so you need a EMI filter. So okay, EMI filter also is considered a size. Okay, and cost also cost of the inverter also will be more. Now opportunity, now when we are talking about drawbacks, so there must be some opportunity to improve. So, okay, so what we can do, we can improve efficiency by reducing conduction and switching loss. Okay, then also we can actually minimize the losses, harmonic losses. We can reduce the EMI filter and DC capacitor size. So as we have seen that, okay, capacitor, DC capacitor size also is important factor. So we can also minimize DC capacitor size, and also we can reduce power module size and weight. We can also minimize EMI to reduce the filter size and increase coolant temperature, and we also can decrease the flow rate, right? So this is the some of the opportunity in this domain. So motivations for employing WBG device in industry. So industry is targeting to achieve a power density of 100 kilowatt per liter. So how we'll achieve? So we have to make our inverter in small size, okay, so that we can make our power dense inverter, right? So lighter weight, so lighter weight, how we'll achieve using our WBG based inverter, right? Okay, and also we want to improve our efficiency. So average efficiency industry is targeting is greater than 97%. Okay, and industry also looking for the solutions where actually you can decrease the motor loss. So there are different types of losses in the motor. So we have to minimize the losses in the motor, and we are also trying to minimize the torque ripple. And we have seen by our research in the inverters, so WBG device based inverters. So if you are trying to advance the technology, and in terms of outcome, you can see that it also reducing the torque ripple in the motor, right? So you can actually achieve through WBG based device, and it is also decreasing cost and weight. So what is the target cost? So we can see here the target cost in terms of power is $4 per kilowatt. So I'm showing you one SiC module, 16 volt Cree SiC module. Okay, so you can always search for Cree Wolfspeed. What kind of modules they are having, or different versions in different module of the inverter. Then also you can get a 650 volt GAN system. So for the more information, you can always visit GAN system. Okay, so they are having different models and with different voltage rating. Now here what we are trying to do, so GaN, so gallium nitride. So gallium nitride actually is promising the best and optimized sizing and performance, right? So how I will show it here. If we compare with the silicon here, my screen is visible, right?
Yes, sir. Yes, sir.
Okay, good, thank you. So here in this diagram you can see that, okay, if we compare with normal silicon based device and gallium nitride based device, you can actually imagine that how we can optimize the size. Here this one is silicon based design, and this one is gallium based design, gallium nitride based. So if we compare both two, so you can see, so maybe 1/3, okay, 1/3 of its design compare with silicon based power supply. Okay, so you can actually save a lot of space. Okay, and you can improve the power density, right? So more efficient, so 1/4 the losses, smaller, 1/4 of the size, okay, so lighter, 1/4 of the weight, and it is having a lower cost, right? So as compared to silicon based device. Here also we are having this gallium nitride. So gallium nitride is promising the best solutions, right? Here also in this diagram also you can see. Now how we'll develop? So okay, we have seen the advantages, features of gallium nitride, silicon carbide. So how we develop our GaN based inverters, how it look like the actual inverter. So I am showing you here. So this is one of the designs from my previous lab. So this is the GaN device you can see here. So these are a very small in size. Okay, so this is the power board. Okay, so here now a point is coming. One point why we go for GaN inverter. So GaN inverter, so wide band gap device. Okay, so we have a lot of features in wide band gap. Okay, so faster switching, it is giving providing us a small size, lighter weight, lower voltage drop, and higher blocking voltage. Sorry, excuse me. Higher operating temperature. Okay, so this is one of the power board of the design WBG based inverter. So especially here we are using as a GaN device. So from the GaN system. Now how high performance versus legacy packaging technology. Okay, you have seen different packaging. Okay, so different modules they are having. So those who are interested to know more about this kind of model, so you can visit a GaN system. So here you can see this is in terms of parasitic inductance and thermal impedance. Okay, so parasitic inductance, so in sorry, excuse me. Now as a researchers in the inverter development, when you are going to provide a better solution, so you always see that we can optimally design our gate driver. So there we have seen that due to parasitic elements, what is the disturbance, and will provide the solutions for that. Okay, now gallium nitride in EV. So here, how it is better? So 8% cost reductions as compared to other models. So here in silicon inverter, so you are getting 15 kilowatt. Okay, so if you see the cost, right? So BOM inverter BOM cost by technology, if you want to compare, so here you will get with the same BOM 15 kilowatt inverter, right? And you can have actually 25 kilowatt with the GaN. So 8% cost reductions is possible with GaN system or GaN device, right? Now here you can see that DC to DC converter, when you are going to design a DC to DC converter, so 100% better power density you can achieve. So here 1 kilowatt per liter, so 93% efficient, water cooled. Here this is with silicon, and this one is with gallium nitride. So this is 2 kilowatt per liter, so that is 90% efficiency, air cooled, and this is also having a lower cost. Now GaN in onboard charger. So just I'm showing you, I will not discuss this part, so charging part. So here just you can see this in terms of size how it is optimized. Okay, so this is with silicon and this is with gallium nitride. Okay, so how much size reductions is possible with our GaN system. Now prototype, coming to the prototype development. So this is one of the prototype development in my previous lab. So here what we have used, so we have used I have shown you the power module. Now this is the driver module. So again, motor drive. So here everything is integrated. Your microcontroller here you have seen. So TMS 2000 series. So we're 3970. Okay, so here we have used this microcontroller, and again motor drive. All the circuit is designed in Altium. Okay, Altium is a PCB design software, so I think all of you know that. Okay, so you can design your own gate driver, you can design your own motor drive. Okay, here so what are the challenges we have faced, and from the challenges, how we modified our uh, design to achieve better performance. Just let's try to understand. So when we were designing, so this is inverter. Okay, so yes, here, yes, this one. Some of you can acknowledge whether I am audible.
Yes, sir. You are audible, sir.
Okay, good. And slides also changing. You can see it clearly. Is
Yes,
it
sir.
visible?
Yes.
Okay,
Yes, sir.
okay. Thank you so much. Because we are in online mode in between, so sorry for that. I'm in between. I'm asking you. Okay, so that the communication, there won't be a communication gap. Okay. Now here, what we have seen when developing our GAN inverters, so we have seen that okay, we are having oscillations in our gate driver. So gate driver oscillations due to what? So we were trying to understand the cause of the oscillations, and we have seen that although we have designed our gate driver perfectly, but due to the parasitic elements we are facing a problem. So these parasitic elements actually creating oscillations in gate driver. So definitely a solutions must be provided to get the better results. So we keep on working in that side, gate driver research. Okay, then we came up with solutions also. So how we for the analysis part, what we have done, we have actually trying to understand how your parasitic elements is actually creating a problem, so how we can measure the parasitic inductance. So here for that we have used Altium export of Q3D. Okay, so Q3D model. So in ANSYS Q3D we have a model, and we are trying to extract the parasitic inductance. So we have seen that okay, so due to that element and using that value we have simulated, and we are trying to minimize the oscillations. So then we come up with some of the solutions, so we'll discuss in the coming slides. So if you try to understand the GAN system reference design, so we, GAN system is having different reference design with them, so you can always visit, and you can find your for your suitable applications. Now another research was going on to get the better performance with the silicon carbide inverter. So what we have done, so if you see here, so this is one of the inverters of silicon carbide inverter from the Cree Wolfspeed. So, excuse me. Oh, please wait a minute. Sorry for the inconvenience. Okay, so in silicon inverter developments, what we have done, so we have taken a base model. Some base models, what was base model? So Cree speed, Cree is providing the one of the best solutions to the automotive industry uh, with their 6 module and 6 based complete inverter. Okay, so this is the automotive grade. So CRD 300 DA A2E, so that is actually comprised consist of XM3. So and gate driver module, so they are having CGD 12 HV XMP gate driver. So they are using this gate driver. And in terms of SIC module, they are actually using CAV 450 M12 XM3. So that is a rating of 1200 volts or 450 amps SIC hub bridge. And how they are controlling, so they are integrating with TMS 320F379. So that is having 200 megahertz frequency, and that is 32-bit processor. So here you can see in controller part, so they are using this microcontroller. So here we can see from this diagram that we are using 3 capacitors, right? So one of the challenges is how we can optimize this capacitor part. Okay, so how we can optimize the design of this capacitor for selection of a new capacitor. So when you are going for a new design, so you have to select one base design and you have to provide your own solution. So they have their own design, so we need to provide better solutions as compared to them. So this was one of the researcher target. Okay, so here gate driver XM3. So for this XM3, what kind of gate driver they are using? CHD12 HBXMP, right? So this is the internal structures of this inverters. In this diagram, you can see this is your speed inverter, right? So this is completely based on silicon carbide. So SiC inverter. Now what we achieved, we have complete, we were trying for the solutions, and what we achieved that. Okay, now so if you incorporate with your gate driver design this IC ADM4135, so this is from analog device. So if you achieve incorporate this IC with this, okay, then you can actually minimize your gate driver oscillation. So due to your due to the Miller effect, actually you are getting oscillations. So we are getting oscillations. So we have minimized this in the simulation stages you have seen. So here we are having gate driver oscillations in gate voltage, but in other results we have seen that we can actually minimize this oscillation. So using ADM M4135 and optimum gate resistance. So what you can do, you can actually work how to select this optimum gate resistance. So you can think of, so whether there is any technology to optimize this gate resistance. Okay, so maybe you can think of machine learning technology, so how to optimize this gate resistance value. So this will be a huge contributions in this research domain. Okay, so gate drivers, once we have minimized the oscillations, then we have seen that we can actually improve the performance of the system. Okay, so I am showing you some of the part of our research labs to give you a glimpse how a biggest electric vehicle research lab is going on. So this is one of the biggest EV research lab under the tier 1 research chair professor in electrical vehicle domain. So you can see here, so they are having all the systems. Okay, here this is the cooling systems I was discussing. So cooling system, industry is providing the cooling system, so with that industrial standard. So Magna Internationals, we were working with Magna Internationals, so they have provided us the cooling systems to test our motor. So this is one test bench. Here you can see So we can test here up to 300 kilowatt motor. So the range is a 300 kilowatt motors we can test here. So this is a huge capability. Yeah. And this is another diagram. And here you can see that, okay, so different motor, different PMSM based research was ongoing here. Okay. So with the semicron inverter and silicon based SiC based inverters, how we proceed step by step. So we have just I'm showing you just glimpse. So we can actually set this kind of lab. If we fix our target, then we can set, and we can contribute a lot in this domain. We can collaborate with the industry, and we can provide a value-added solutions to the industry. So here, this is the design motors in our lab. Okay, so this is our own design. So and the productions. Okay, so here you can see these are the arrangement for cooling. Okay. Okay. So we'll take a 1 minute break, then we'll start our next part of this session. So that is intelligence ATDS system. Okay. So just we have a continuous sessions. Just a short break. You can take a 1 minute short break. Then we'll discuss our intelligent ATDS.
Okay.
Be online. Okay. So you just within a minute will join.
Okay. Okay.
Okay, sir.
Okay, so we'll start our next part of our discussion. Oh, Anil, am I audible?
Yes, sir, you are audible.
Okay, I think all of you are here. Okay, so this is a quite interesting topic. So as the whole world is going in this direction, so intelligent ATDS, right? So intelligent ATDS system. So how we are going to make our intelligent electrical traction drive system, right? So if you talk about artificial intelligence, so just we are actually, what we are trying to do, we are actually trying to create a intelligence in our machine. Okay, so in our controller, as electrical engineers, what we are trying to do, so we are trying to incorporate the intelligence in our control algorithm, so that it can take the decision, okay, and it can produce our desired output. Okay, so this is our main target, right? So let's see one by one how we can achieve our target. So we'll using our intelligent ETDS system. So just if you see in these diagrams, so artificial intelligence is basically mainly the concept of creating artificial human brain. So as we know that, okay, so from the childhood we are getting trained and we are acting accordingly, okay, and sometimes we don't have the past experience, however we have to take the decisions, we have to act as per the situation. So we are actually trying to incorporate the control algorithm in our drive system, which actually match like this. Okay, so we are trying to work in this direction. So we are trying to replicate our human brain. So here you can see, so in this diagram, so this is just it's clearly depicts the concept of artificial intelligence. So we are actually trying to replicate our human brain so that it can take decisions efficiently, right? So if you talk about artificial intelligence, so when electricity came, it completely changed the world. So in artificial intelligence now also going to change the world completely. So using artificial intelligence, we are going to create a different world. So how we are going to create, so if you see anywhere surrounding you, so you can find that there is a possibility to implement or incorporate the artificial intelligence technique. Okay, so we'll see one by one. So what is the opportunity we have where we can contribute, and as an electrical engineering researcher or as a EV researchers, how we can contribute using our artificial intelligence concept. So here there are a few applications of AI. So apart from that, whatever you will think, then you will have a applications of AI in that. Okay, so you just think, just name one thing, so you might find, okay, so there may be applications of AI. So here you can see Tesla. So Tesla Motors, so they are actually trying to incorporate machine learning technology in their control algorithm. So how they can actually improve the efficiency in motor control. Now here in automated driving system also, people are using artificial intelligence. In medical sector, say there is a lot of applications of artificial intelligence. Okay, so now if we go for our grandfathers or uh, old people cataract operations, there also will find that there is a huge applications of artificial intelligence in cataract operations. Also there is some technologies coming, they are actually promoting, doctors are promoting that, okay, using artificial intelligence we can give you the better solutions, and this is already in the market. right? And so there is a lot of applications in robotics, especially in robotics. There is huge applications of artificial intelligence. So we are trying to make the robot intelligent so they can act efficiently, right? So here in application industry, in tractions, and aerospace, so everywhere we are trying to contribute using our artificial intelligence. Okay, and different space agency also, they're trying to predict some of the things using their artificial intelligence. Now this is a simplified canonical architectures. Okay, so why? So here we are having some sensors, we are taking some data, so data conditioning, then we have informations, then we are processing these algorithms, so then we have HMI. Okay, so or we are trying to interact so with the different applications, so different plant model. So, and these are the few advancements in modern computing technology. We are the modern computing technology, we are in simple words we're calling it as workstation. So it is coming with the GPU, TPU. Okay, so there are advancement in computing also. So here a few of the applications you can say. So this is a simplified canonical architectures, right? So now the point is, why AI now? So if you think once, just take a minute and think, why AI now? So whether this concept is coming from long time, yes, the concept was there, but why AI now? So we are having a big data everywhere. So big data everywhere, and nowadays with the advancement in computer domain, so we are having a advanced computer power, and we need computers where we can implement those algorithms. So there are a lot of machine learning advancement in machine learning algorithm. In combinations, we can actually provide solutions, right? So solutions to all the sectors, from medical sector to automotive sector, everywhere we can provide a AI based solutions, right? Now we have discussed the ETDS systems. Now we are going to discuss intelligent ETDS systems. So what is the additional part here? So here we are actually uh, incorporating our intelligence e-drive systems here, right? So you can see, so we are having PMSM, we are having WBG inverters, so we make the EV systems efficient. After that, we are making that efficient. We are again improving the efficiency by incorporating the intelligent e-drive system. Intelligent e-drive systems improve performance in dynamic speed and torque conditions, and it is having a fast current response, and it also reduces the computational time. Okay. Now, if you consider the potential of intelligent control, the research idea converges on ML-based control for ETDS, so which is actually reducing the switching loss, competition time, and to enhance the transient performance of ETDS by incorporating machine learning based parameter independent control. So that part we'll see. Okay, so generally if you are working in electric vehicle domain, you might have faced. Okay, so due to the parameter change, okay, so we have a PI controller, so it is having a parameter dependency. So we are actually going to provide a solutions, a parameter independent controller, right? So here actually we are putting into the heart of the control systems, so we are calling it as intelligent e-drives by incorporating machine learning technology. Especially we are working in this reinforcement learning based technology. So their incoming slides will try to understand in more details what is the technology. So here we are trying to develop a deep neural network control for ETDS systems. So this is a simplified block diagram. So we have electric traction drive. then this is your RL agent. Okay, so in reinforcement learning, we have an agent and we have some policy. So we have to fix some policy and we have a RL algorithm. So the concept I'm telling you, so what is the concept behind that? So how it works now, when you are talking about actor and critic based algorithm, so it actually based on the concept, like when we are training our children or our kids, so that times in initial stage we used to say, okay, you do your homework, I'll give you a toffee, right? So children are interested that times for getting that toffee, they will do their homework. So it means we are giving a reward to that child and that child is working, right? So working accordingly. Now sometimes also when we are training our children, so our kids, so that times we are giving a punishment. What kind of punishment? In terms of punishment, okay, so for their benefit only. So okay, if you don't follow or if you do any mistakes, then you have to stand, okay, for 1 hour. So this is the penalty we are giving. So this is a concept, that concept has been taken from there and we are actually trying to incorporate actor and critic based network system. So that this is nothing but reward and reward based systems. Like when your algorithm is following that path, then it will collect some rewards. Now if it is not going in opposite directions, so then we will penalize that. Then once you penalize, then it will try to change its path, then it will come into the right path. So this is the concept behind the actor and critic space network. So what we are doing here in the policy, so we are actually setting some policy. Okay, so if it happened, if it is the input, then output should be this, otherwise you update the algorithm. Simple. So based on this only we are working. And this is based on deep neural network, so DNN, right? So why this is required? The effective tuning of PI control parameters depend on planned parameters. Now those who are working in this area, we have seen that, okay, so to tune our PI controller perfectly, we need the informations about the planned parameters. Now here we can see the performance. Due to the performance and drawback legacy of PI controller, so we are going for DNN based. So in DNN based, and especially in reinforcement learning, we'll see that, okay, it is a parameter independent system. So what it will do, it will try to learn from the environment. Okay, so it will learn from the environment and it will act accordingly. Okay, and the goal of the intelligent control is to learn the best function by interacting with the environment and to provide the optimal actions. Here what is observations? The observation retrieve features from the environment and the action is control signals from the controller. Actions is control signals from the controller and RT is the reward functions. Okay, so from here you are getting a reward, right? So this is another simplified block diagram. So here this is your intelligent control we are going to use. So here this is your environment, so observations, and it is going to act. The goal of the intelligent controller is to learn the best function of by interacting with the environment and to provide the solutions. And this is the internal structures of the neural network. Okay, now we are at when we are talking about drive systems, so let's try to understand in deep into the drive system. So we are having a motor PMSM, then we have a inverter, so we need to generate the control pulse to the inverter. So how we are actually doing, so we want to control, we want to provide the best solutions. So here we are having a speed reference and we are sensing the actual speed, then we having a PI controller. After that we are generating our reference current. Then here we are actually incorporating DRL based current controller. So in DRL based current controller, what we are doing, so we have a reward calculations and we have an actor critic network in RL agent. So from there, what we are actually doing, so we are generating VD, VQ and IDIQ, and after that, all we know how to generate the PWM pulse and all. So here we are actually replacing our PI controller, and this control techniques is parameter independent control, right? So these are the few results. We can see that we can actually minimize the overshoot and transient time, and this is also learning from the environment. So what we can do, so after this, let's charge up to change the world. So we always try to contribute from our side in electrical vehicle domain through our research. So either it may be inverter development part, it may be by providing intelligent solutions, or some of you can work in battery domain and designing in BMS systems, intelligent BMS system, or you can design a efficient motor. So we always contribute. So let's charge up to change the world. So what is India is focusing on EV. So there are a lot of news is ongoing. Okay, so that government is providing so many facility to the researcher, and they're targeting to incorporate the EV technology. So as a beginner, how we can develop yourselves, those who are beginner in the sessions, so how we can develop your skills, so you can be a master of this software packages, or in terms of controllers you can have the knowledge of DSP or microcontroller, I can say. So here you can learn FPGA, because anyway in inverter, in electrical vehicle, all the algorithms we are going to implement either in microcontroller or FPGA. Okay, so we are having OpenRT. Okay, so in advanced research levels if you go, so you have this space and OpenRT, and the latest technology is also coming, speed goat. Okay, so if you search, we are also having OpenRT speed goat technology. There a lot of research facility is also providing, they are providing, so you can have a complete knowledge in this direction, so you can contribute a lot in electric vehicle domain. And also along with that, you can work in the software packages like Plex. Okay, Plex is one of the best software packages for power electronics based simulations and PCing. Then you can go for Spice, MATLAB already all of you are using. Then Speed is one of the machine design software. Then you can have ANSYS experience, then a LabVIEW, and then an Altium and other PCB design software. And apart from that, you can always try for other facility also, like in ANI systems they are having ANI Serio 9045 or higher versions. So those kind of things also you can get experience. Okay, so these are the skills you can develop uh, as a researcher. Okay, so how it will proceed, so you can make a collaborations or connections with different industry, like in this domains we have Mahindra Electric, so they are also open to make a collaboration, Tata Powers, Magna International. Then we have in Infineon, Nidec, Cree USA, Gan System USA, Ford, Tesla, General Motors, Semicron, Eaton, G, all the companies are open nowadays. So they are also trying to collaborate. So what we can do, we can actually approach the industry. Let's make a collaborative research. So that will have a value added research result, productive research results for our society. So always collaborations and connections is required. So collaborations between different academic institutions, collaborations between different academic and industry. So this is one of the vital things we need to consider, say, for our future research in this domain. Now, research facility development, how will work? So basically, initially we may not have the complete research facility. So how will grow? So as we know that first to grow if you want to get the fruits, so first you have to first you need a seeds. Okay, so first that seeds, you have to find that seeds, what is the perfect seeds for you. Either you are going to work or we are going to develop a facility with these kind of systems like OpenRT, or you can use a microcontroller or speed code. So you just get that one, and what are the different components you have. Then gradually your lab will be developed, or your research lab will be developed, and also you are collaborating with the industry, and you can make a big lab, right? So initially we may not have that facility, but we have to keep on working to develop this facility. So this is my experience, what I have seen. So if you want this fruit, so you have to get the perfect seeds first. Yes, career perspective, throughout all this research, you can go for R&D, research and development. So in automotive industry, especially in automotive industry, also if you have excellent research capability in inverter development, so you can also go for power and energy sector and space agency as well. Okay, so with that I'm concluding here. Thank you so much for joining my session. Thank you.
Thank you, sir. Participants, any queries you have, you can ask.
Good afternoon, sir.
Yes, good afternoon.
Sir, we are working on the sensorless induction machine control application.
Yes, good, great to know.
So we are newly using new controller, like a Wave CT controller, WaveIT.
Okay.
So what is the difference between different controllers? Suppose you have just explained D-Space and other controllers, microcontroller, FPGA based controller.
Okay, so if we are talking about different types of controllers, so there so specific controller is having specific operation capability. Like for example, if you are comparing with OpenRT with microcontroller, so you will find that in OpenRT what you can do, you can actually let me go back to my slides, then it will be clear for you. Just wait a minute, right? As a plant model. Okay, and you can do either SIL or HIL, hardware in loop, or power hardware in loop. Okay, and all the real-time applications you can get. For example, you don't have machines for now. Okay, you can actually do in OpenRT. So, okay, you can get real-time results from there. Okay, so how will you do? So machine models will be in plant. Okay, so in FPGA or other control algorithms, so you are having these options like in FPGA, in case of OpenRT, and speed code also is providing, like they are actually providing emulations capability, like battery you can emulate, right? So battery model complete, if you don't have a physical battery systems, then also actually you get the characteristics from there. So they are having this capability with them. And in terms of specifications also, if you see, so different microcontroller is having different operating range. Okay, so that is one of the difference. So in OpenRT or SpeedGoat, you have larger research scope, okay, as compared to your microcontroller or FPGA.
So the same algorithm we can also develop in the same different controllers. So shall we produce the research papers on that?
Yes, yes, you can produce.
So same algorithms. we are using same algorithm. We have already tested in this space. The same algorithm shall be produced at, shall we make it prepare at the Wavect Netlink controller, recently popular in power control application.
No, it's not like that. Okay, you have done, someone has done in this space, and now you are using some other controller, and the same results you can produce as a paper. No, you have to contribute from your side. Okay, so some novelty or some delta advancement in your research domain, you have to provide, then you can publish.
Okay, thank you, sir.
Okay. Okay, I think we are good for today.
Yes, sir. Thank you, sir, for giving us a clear view of advancement of EV technology and the role of wide band gap device in the improvement of efficiency, switching frequency, and size of E converters in EVs. Sir, you explained in detail about GAN and SiC based converter modules, gate driver issues, intelligent controllers. Your session was very informative and very knowledgeable, sir. Recent developments, you talked about recent developments. Thank you, sir, for sparing time for us in this busy schedule. Thank you so much.
Thank you all. Have a great day, and please be safe and take care. Thank you.
Thank you, sir. Good evening, sir.
Yes, good evening.
Good evening, sir. Sir, with your permission, can we start our session, sir?
Yes, sure. Still you can start.
Yeah. So, good evening, sir. Welcome to the FDP program on recent trends of control system in power electronic converters. It gives me immense pleasure to introduce about our eminent expert of our today's technical session 12, Dr. Arvind Panda, sir. Sir is assistant professor at NIT Sikkim. He received his BTech degree in electrical engineering from BPUT Odisha in 2006, MTech and PhD from IIT Roorkee in 2009 and 2016 respectively. Sir has published around 20 papers in various international journals and conferences. His research interest includes power electronics, electrical drives, electrical machines, PV, DG systems. With this brief introduction, I would like to hand over the session to Sir for further proceedings.
Yes, thank you for the introduction. And first of all, I would like to thank the organizing committee, especially Professor Mrinal Sarkar, for giving me this opportunity. For today's session, let me share the slide first. Just a minute.
Okay, sir.
I hope it is visible to all of you.
Yes, sir.
Yes, shall I start? Is it visible? Screen is visible?
Yes, it's visible, sir. It's visible, sir. You can start.
Okay, thank you. Basically, for this today's talk, I'm going to give a talk on enhanced power quality based grid type PV system for plug-in electric vehicle. Actually, I have divided this topic into two parts. First, what is the need of electric vehicle at the present moment, and when we go for charging of electric vehicle, what are the power qualities we face, and how to mitigate those harmonic and also how to compensate the reactive power. That basically I'm going to cover. So the topic is like this: enhanced power quality based grid type PV system for a plug-in electric vehicle. Just a minute. The slides are not changing. Okay. I think there was some problem. Okay. Before going into this topic, let me show you some pictures. This is basically some pictures of Indian Ocean tsunami that killed nearly 230,000 people in the year 2004. Basically, before going into EV, let me show you some picture to get some motivation behind this topic. So these are the pictures of that Indian Ocean tsunami. And after this tsunami, the scientist warns that yes, such type of tsunami will be more common in future. And we saw even after 2004 also, we saw some tsunami that occurred in Japan and some other places also, right? Then also at that time, after the tsunami, some researchers like Dr. Robert Weiss of Virginia Polytech Institute he said that based on their research, it shows that the sea level rise can significantly increase the tsunami hazard which means that smaller tsunami in future can have the same adverse impact as big tsunami that occurred in the year 2004. Similarly, let me show you some other natural calamity which occurred in the year 2013 in Uttarakhand, which is basically Uttarakhand flood. And these are some pictures of that horrific incident which was part of this Uttarakhand flood in the year 2013. And it basically, based on official data, it basically affected around 4,000 or 5,000 villages and caused more than 10,000 deaths. These were only official data, and unofficially, we had lost more than 70 to 80,000 lives, right? So this particular disaster occurred at Kedarnath. Basically, this was because of rapid melting of ice and snow on the Kedarnath mountain, which is 6 kilometers from the temple. And this is also, you can say that, because of global warming only, right? Then you might have remembered recently, in the year 2020, there was a forest burn in Australia. And again, the scientists want that the climate change will make fire-prone condition like this, which occurred in the year 2020, more common in future also. So we'll see such type of calamity, natural calamity, or such type of forest burn in the coming years also, because of the climate change. Then cyclone. India have witnessed around 117 cyclones in last 5 decades, and we have lost so many lives, right? So what are the reason behind these natural calamity? As we know, the main reason behind all such type of natural calamities, natural disasters, are basically global warming, right? Climate change. So if we conclude here, then you can say that energy and environment, particularly the global warming problem due to these man-made greenhouse gases, are basically the serious concern in our society, and that nowadays almost everyone is in the world is talking about it. So how to mitigate this global warming problem? How to what are the thing based on what are the thing we have to what is our contribution to limit this global warming issues, right? So we have to work in this area. And there is no doubt that energy has been a lifeblood in the evolution of our industrial civilization, and you can say that per capita energy consumption has been the barometer of nation prosperity. So the nation which is consuming more energy per head or per capita are termed as a basically more developed country, right? So the thing is, what is global energy generation scenario, right? We saw the problems due to climate change, due to the global warming issues, right? Now let us move into the global energy generation scenario. As we know, the most of the at this moment, this is the data from International Energy Agency, and based on this, we can say that till now we have majorly depend upon the fossil fuel based energy sources for generation of our electrical energy. And you can see here the contribution of coal is still 54.2%. And even though in last since last 1 decade we are more focusing on renewable energy sources, but still the contribution is majorly from the fossil fuel based energy sources. And basically whenever we burn this, whenever we use such type of energy sources, it gives rise to many pollutant, mainly carbon dioxide, and these are the major cause of global warming. So in order to limit this global warming issue, this climate change issue, we have to focus, or we have to switch ourselves from fossil fuel based energy sources to renewable energy sources, right? So this is one point. So we have to move from fossil fuel based energy sources to renewable energy sources. The second is, what is the contribution of transport sector in global carbon dioxide emission? So if you see the data, this is the data from the I got this from World in Data website, and based on this, you can say that out of total global carbon dioxide emission, basically 74.5% is basically from transport sector, right? So the majorly, basically you can say that the transport sector is contributing largely on the carbon dioxide emission, right? So if we able to limit this carbon dioxide emission from the transport sector, you can say that somehow you can minimize or mitigate the climate change issue, or what you can say, global warming issues. So to take out some points how to solve or mitigate the climate change problem. So first thing, we all know that we have to promote our energy consumption in electrical form, right? We have to cut down or eliminate the coal-fired or oil-based power generation. And mostly we have to focus on renewable type, like solar, wind type energy generation. Then again, we have to preserve rainforest in the world, and we have also to promote widespread forestation. Then, as I mentioned, we have to promote the generation of environmentally clean energy sources. Then, with reference to today's talk, we'll discuss majorly on this topic only. So we have to replace the internal combustion engine based vehicle by electric vehicle. So this is one way by which we can limit or we can mitigate the climate change problem somehow. And lastly, we have to save energy by more efficient generation, transmission, distribution, and utilization of electricity. So these are some points by which we can solve or mitigate the climate change problem. Now, the thing is, why so much interest in EV in India? If you see the data from WHO, World Health Organization, based on their data, you can see that 14 out of the world most polluted 20 city, out of 20 city, 14 are from India only. So this is a big concern for all of us, right? Then if you also see, that means not only pollution, majorly whatever oil we are consuming or for our transport sector, mostly we are importing 70% of the petroleum or oil from other countries only. That means it is heavily affecting our GDP also, right? So our consumption is more as compared to our production, and majorly we are depending upon the other countries. and we are importing the oil from other countries, right? So one thing is already more out of you can see that pollution is more out of most polluted 20 cities of the world, 14 are from India only. Second is we are heavily depending upon other countries. That means we are importing the fuel, the oil, the petroleum from other countries. That means it is also affecting the GDP. So based on this two major point, we can say that India, or we have to move from IC engine based vehicle to electric vehicle as quickly as possible, right? Because now this is the high time. Both actually there is shortage of petroleum, the oils, and also the climate is changing drastically, right? So we can limit all these things. That means we can limit this global warming problem, and also in order to have self-sustain in this, even in the transport sector, we have to replace the IC engine based vehicle by electric vehicle, and with this the oil import will be go down drastically. The pollution control objective of government of India can be attained, right? And as we know that in electric vehicle is more 4 times more energy efficient as compared to IC engine based vehicle. This is because less in electric vehicle we're having less moving parts, right? And also compared to if you see IC engine based vehicle or IC engine is having efficiency of 12 to 22 to 24%, whereas electric motor, whatever motor we use in electric vehicle, its efficiency is around 90%. So with this application we can with these advantages of electric vehicle, so now it is the time to move from IC engine based vehicle to electric vehicle as early as possible. So more research are going on in this sector, or in this in the area of you can say that in the sub area of electric vehicles are basically battery management system, the motor control of electric vehicle on the battery side, right? I'll come into it. So these are the motivations. This vehicle. So, but we are not able to quickly move from IC engine based vehicle to electric vehicle. What are the infrastructural hurdles? As you know, Government of India is targeting to switch from IC engine based vehicle to electric vehicle majorly. Want to switch from IC engine based vehicle to electric vehicle by 2030. They are targeting the year to 2030. What is the reason behind that? Because many companies have launched their electric vehicle, but why Government of India is still targeting the year 2030? Why not before that? There are some infrastructural hurdles. If you see the thing is, as per Government of India, 30% of vehicles on road to be electric by 2030. But in order to have these many electric vehicle to be run in, we should also have sufficient electrical energy, right? So if you see in order to run this much amount of electric vehicle will require 16,000 crore units. That means the power demand will this moment we don't have that much amount of energy generation so that we can immediately switch from IC engine based vehicle to electric vehicle, right? So first we have to produce that much amount of electrical energy from IC engine based vehicle to electric vehicle. So at this moment, or this is basically data from 2018. On 2018, you can say that we were around 900 crores unit of electricity we were shortfall. So because of this issues, we are slowly trying to shift from IC engine based vehicle to electric vehicle. First, we have to create that infrastructure. We have to have that much amount of electrical energy to charge our electric vehicle, right? So one infrastructural hurdle is power generation, right? So once we have that much amount, as I mentioned earlier, also we have to think about global energy issues. So we cannot heavily depend upon the coal-based energy generation, thermal power generation, right? So even we are thinking to move from this thermal-based power generation to maybe renewable energy power generation or fossil fuel-based renewable based power generation by using some wind energy or solar energy, right? So once we will able to generate that much amount of electrical energy as required by uh, uh, as required by our of India, then only we can say that yes, now it is the time we can move from IC engine based vehicle to electric vehicle. Yes, obviously, there are some issues in electric vehicle also, but you can say that at this moment in 2022 or even in the last year 2021-22, you might have seen so many companies have already launched electric vehicle, right? But completely it is not the time by which we can switch from IC engine based vehicle to electric vehicle, right? As I mentioned, one is infrastructure hurdle is power generation. We don't have that much amount of power generation. And second is in order to create the charging infrastructure, it requires around 12.5 trillion. You have to invest. India also have to create that much amount of charging infrastructure, and so that's why the government of India 2030. So by 2030, both power generation side and even for in the form of charging infrastructure side will be ready, right? So these are the two infrastructure which have to work on some types of energy sources that like solar or wind. How can we use those energy sources to charge the electric vehicle, right? Whenever we the grid, right? We will also have to
Sir,
Yes. Now,
Sir, there is some-
at this moment, yes.
there is some issue with the voice, sir. The break is there in between, that's why. Due to, I think, the
Now is
connection.
it fine?
Now it is okay, sir. Like earlier there was break in between. Means in the sense the cracking, the voice like breaking is coming.
Okay, please, whenever again, if it occurs, then please let me know.
Okay, sir.
Okay. Now, at this moment, there are lowest one is 5 to 7 lakhs, and okay, an average. So the major issues in electric vehicle is the battery size. At this moment, the battery size and the travel range. So if you see, Hyundai is whatever electric launch, its travel range is right. Basically, this battery is playing a big role in the cost of the electric vehicle. That means not only cost, also there is some inconvenience in the charging of the battery of electric vehicle also, because charging time is also more, and the range is also not in the higher side. So basically, there are two issues at this moment in electric vehicle. One is a size of the battery, right, and travel range. So whatever electric vehicle have been launched till now, even though the cost is more basically because of the cost of the battery, and even after spending uh, so much amount of money in electric vehicle, we are not able to get range, right? So the travel range basically. So there are some issues, and once we can have the battery which with high you can say energy density, then we can solve this problem also. Travel range can also be improved, and also battery size works are going on both on the energy density side and volumetric energy density, both on range and size side. So hopefully in 1 or 2 years we'll get the batteries which can have high, which can give you high travel range also, right? And cost will also reduce. Now, as we know, as when we are moving from IC engine based vehicle to electric vehicle, so in IC engine based vehicle, the energy source is basically we are having a electrical fuel pump of not that much bigger size, and basically we store petrol or diesel, and those are the sources for this IC engine based vehicle. And now we are replacing this by electric vehicle, and the major source of energy for this electric vehicle is basically your battery, right? Now the problem with this electric vehicle, as I mentioned, higher weight, also higher cost. Obviously, a higher weight means the requirement of material is also more. That's why the higher weight is coming into and size is also more, and basically these two things are so these are the three issues, and whenever weight is more and the mileage of any vehicle, you can say that which also depends upon the weight of the complete vehicle. So indirectly, the higher weight of the battery is also one of the reason because of which we are not even getting the higher travel range. Other than the switch weight, volume, and cost of energy storage, that is batteries, right? So till now we have seen some problems. Why the problem? Why we are not able to quickly move from IC engine based vehicle to electric vehicle is fast is especially for in India case. We don't have that much infrastructure, charging infrastructure. The power generation also one concern, right? Then the other issues in electric vehicle is basically the battery. The weight, volume, and cost of energy storage, that is battery, is more. And once we'll have a battery of high gravitational energy density, right? Means, as you know, gravitational energy density means it is the measure of how much energy a battery contain in proportion to its weight. So if we can able to reduce the weight and with reduced weight, if we have sufficient amount of energy, then in that way we can say that weight of the battery will also minimize, reduce. And this can be achieved only when whatever materials we are going to use for the battery will reduce. So if materials will reduce, yes, automatically weight will also reduce, and also cost will also reduce, right? So at this moment, the gravitational energy density, whatever battery, lithium ion battery we are using, its gravitational energy density is also more, and also the volumetric energy density. What is this volumetric energy density? It is the amount of energy in a certain volume for a given material, right? So both size and weight are more at this moment for whatever lithium ion battery we are using for electric vehicle case. So more works are needed in this area also. That means in the battery side. So if we will able to reduce the cost of the battery, reduce the both on basically at this moment the major factor that is affecting the cost of the electric vehicle is battery only. Other things are okay. We are having high efficient energy motors, right? Sorry, electrical motors, and only thing is the cost is basically in the hand of battery only. So once the both weight and cost of the battery will reduce, then you can say that EV will be more cheaper than even the present IC engine based vehicle. Right. Now, if you talk about the gravitational energy density content of some fuel, you can see 1 liter of petrol can give you 12.5 kilowatt hour energy. Similarly, let me talk about only petrol, diesel, and there is one more options we are having, hydrogen based fuel. So 1 liter of petrol can give you 12.5 kilowatt hour energy. Similarly, diesel oil can have can give you 14 kilowatt hour per energy. And what about the energy density of battery at this moment? Whatever batteries are available in the market, this is the data of 2020. So based on 2020 data, whatever battery we are having, that can give you in the range of 300 watt hour of energy per kg, and the sale price per kilowatt hour is 8,000, around 8,000 rupees, right? So if you compare it from the year 2011, you can see the difference. In the year 2011, whatever energy density of the battery was, it was in the range of 80 to 100 watt hour per kg. That means per kg of battery we were getting around 80 watt hour per energy, and in the year 2020 the same, with 1 kg we are getting 310 watt hour per energy. And you can see here in the right side, the price is also drastically falling, right? So with increase in energy density, price is also falling. So in the year so we are improving. The research on the battery side is also going on, and hopefully by 2020, in next 2-3 years, we'll have battery with energy density more than or around 500 watt hour, and its cost will also be in the range of 3,000 or 4,000 rupees, right? So we are having problem in the battery side, both gravitational energy density and volumetric energy density side, and we are moving in the right track, right? So till 2020, whatever battery we are having, its energy density is also around 300, and we are targeting the battery with energy density in the range of 500 or something. And if the cost will also be in the range of 2,000 or 3,000 rupees, then you can say that yes, now it is the time everyone can afford an electric vehicle. So, but why only? Why in the previous slide I told that we are targeting around 500 or 600 watt hour per kg, because we cannot we cannot increase the energy more than, actually we have to keep our energy within a range, otherwise there will be safety concern also, right? In a small container you cannot put so much amount of energy, right? So we have to limit that energy density also, means within a limit we have to keep the energy density, so that there will not be any safety issues also, right? So but still we have to increase the energy density, and it should be around 600, 500, 600 or 700 maximum, right? In that way we have to go. Now if I conclude here, if I make a comparison between the battery and the energy density of petrol, so petrol energy density is around 12,500 watt hour per kg, as I mentioned. But as we know that even in the IC engine based electric vehicle is having, sorry, IC engine based vehicle is having more moving part, so its efficiency is not that much good, right? So even by taking into account 4 times higher drive efficiency of electric vehicle as compared to your IC engine based vehicle, yes, you can say that if you make a comparison at this moment between petrol energy density and whatever battery we are having its energy density, on that side, yes, I see petrol based vehicle or diesel based vehicle is having more energy, right? But on a long term, you can say that if we able to reduce the weight of the battery, if you able to get a battery having energy density in the range of 500 to 600 or even 700, I can say, in the long term, the lithium ion battery based or electric vehicle will have will more profitable, right? So now not only in the cost point of view, also we have to think about the pollution, right? So in that way, overall you can say that ev based electric vehicle will be more profitable, right? Now we saw some advantages and disadvantages of electric vehicle, and we saw the challenges of electric vehicle also. What are the infrastructural hurdles and what are the problem we are facing at this moment in uh, battery side also. One more issue in electric vehicle at this moment is the charging. Charging time is also more, right? Whenever at this moment, whenever we are using an IC engine based vehicle or petrol or fuel based vehicle, yes, for refilling of fuel, it hardly take 5 minutes or maximum. If you consider the waiting time, also 5 to 10 minutes, right? But the same thing whenever we will go for electric vehicle, the case is different. The charging time is more. At least if you talk about a fast charging station, you can say that for whatever charging station we are having at this moment, whatever fast charging station we are having, even that type of charging around 30 minutes, half an hour, 20 to 30 minutes to charge it, to have 80% charge, right? Whatever capacity of the battery we are having, we can charge 80% of it in 30 minutes. So these are this is basically whenever we are using fast charging station. And if you talk about the other charging station like level 1 or level 2 charging station, yes, even the charging time is more than 6 or 7 hours, right? So so the owner of the vehicle cannot wait this much amount of time for the charging of vehicle EV. Actually, it should also be convenient. Like IC engine based vehicle, here also we want to as fast as possible. So let me add, this is also one infrastructural hurdle, and this is also a scope of research. How to that means fast charging. So we want okay, in 5 minutes or 10 minutes it is not possible. At least 15 to 20 minutes can we charge our EV within this 15-20 minutes time, right? So this is also one problem. So now, as I mentioned in the earlier slide, basically in the infrastructural hurdle part, one is power generation. We have to have a sufficient amount of energy generation to have or to meet the electricity demand of this charging station, right? So and also if you talk about the global warming issues, and then we also think about the other type of energy sources, that means renewable energy sources. We have to use these renewable energy sources also to meet the energy demand of the charging station. And also in addition to this, if you use such type of charging station, renewable based charging station, then not only you can meet the energy demand of the electric vehicle, and also you can say that global warming or climate change issue can be mitigated, right? So there are actually already many PV based charging stations have been developed. If you talk about a charging station of electric vehicle, then yes, different types of charging station are there: onboard charging station, off-board charging station, and the infrastructure requirement, and what are the things basically required for to create this charging station is basically, yes, we need some energy conversion circuit or power electronic converter circuit, like um, based on the type of sources we have to use either AC to DC converter, then some DC to DC converter, or again DC to AC inverters. That means all these all are basically power electronic converter circuit, and these circuits are required based on the type of sources we are having available with us, and based on the type of motor we are using, right? And for charging of battery, basically, yes, we'll have to use some DC to DC converter, maybe unidirectional or bidirectional converters, right? Majorly we use bidirectional converter because we'll also we also basically use the electric braking operation, based on our electric braking operation, dynamic braking operation. We also use that energy to charge the battery. So many power electronic converter circuits are used when in the charging station, right? And that means, as we know that whatever power electronic devices we use, whatever switches we use in this power electronic circuit, all are basically non-linear devices, and these non-linear devices basically draw non-sinusoidal current from the grid, the source, and it basically impact the power quality at the grid side. That means it drastically deteriorate the power factor at the grid side, right? That means at the point of common coupling, and also because of this this type of infrastructure in charging station, and basically other customers who are connected at CC also, they also don't get a pure form of electrical energy, right? So that means this type of charging station have a major impact on the power quality of the grid, right? So how to solve this issue? The thing is, I'll show you in the picture in the coming slides. One thing is, we have to move from the conventional conventional based power generation to renewable based power generation. That means whenever because charging station will also have a sufficient power rating, and that means the power requirement is more in the charging station in the future. Not I'm not talking about the charging station which we are having at this moment, whenever we'll have more electric vehicle, then at that time, you can say that like petrol pump these days in every 5 to 10 kilometers distance we will have charging station, and this fast charging station will have sufficient power capacity, right? So many power electronics non-linear devices will be connected there, right? And basically, whenever we'll talk about the power generation for such type of charging station, basically distributed type generation system will be more convenient. So we'll have to use not only in the global warming point of view, climate change point of view, but also it will minimize the losses, right? If you generate the electricity at the site of the charging station, then directly by using any renewable energy source, but mostly solar based power generation is more convenient. So we can generate the electricity at that particular site only, site of the charging station, and that we can use for the charging of our electric vehicle. And yes, if we have excess amount of power generation at any particular instant, we can feed that energy to the grid, right? That means interconnected system. So what are the advantages of these distributed generation systems? Yes, we can reduce the transmission and distribution losses. Yes, then yes, remotely in the remote places also we can have our charging station. So linking the remote and inaccessible areas can be convenient now, and faster response to new power demand like this charging station. And also we can improve the supply reliability, right? And but as I mentioned, there are some disadvantages like power quality issues. So majorly in distributed generation system for power conversion, right? From one type to other type, will use many power electronics devices and circuits, so which are non-linear types, and also most of the loads are these days non-linear types load only. So they have power quality issues in the grid, right? And there will be some synchronization issue whenever we are interconnecting distributed generation system with the utility grid. There will be some interconnection issues, synchronization issues, right? So some disadvantages are also there, but but whatever may be the disadvantages, we have to have or we have to move to this type of charging station only, distributed generation based charging station, right? And today I have even wind based distributed generation system is also possible, but the advantages of photovoltaic based distributed generation system or solar based distributed generation system is like other renewable energy sources, it is also having same uh, it causes no pollution, it is a clean form of energy, and low maintenance compared to other type of renewable energy sources, and in turn it gives high returns, right? But also we are having some disadvantages of photovoltaic based DG system, which we are proposing for our charging station. The installation cost is high. Then you cannot predict the energy generation, right? It is intermittent basically, and in order to have more reliable type PVDG system or photovoltaic generation system, you have to interconnect your photovoltaic generation system with your utility grid, and it is completely basically depends on the climate, so fluctuation will be there. And if you want to store energy from in the daytime, you will have to use battery. So there are some advantages, but yes, there are some disadvantages also. And with this, let me show you the system in block diagram form. Suppose we are having the PV module here on the left side. Then if we are converting it into AC form, so as we know, whatever energy we get from PV module, it is in the DC form. So we have to convert it into AC form. And here, suppose you are having our charging station, EV charging station, right? Or also you can say that the local load of the charging station, right? So on left side, on the left hand side, we are having the based power generation. On the right hand side, we are having utility grid, and in between, we are having our charging station with so many local load. So so many cases you will have, like at any instant you can say that weather is favorable, like in the daytime PV is generating sufficient amount of energy, and suppose the charging station demand is also less, like suppose then you can say that this is the favorable condition, and at this moment or at this time, your generation from PV module is more as compared to the load demand of the charging station. So you can the surplus energy you can feed to the grid. So this is one case. Second case is suppose weather is not favorable, right? And or you can say that you are having so many loads at the charging station. You are having so many vehicle at a time. You are charging so many vehicles, EVs. So either during overload condition or during unfavorable atmospheric condition, if your PV generation is not sufficient, in that case, you have to take the remaining power from the utility grid, right? Like here you can see, combinedly the PV generation and grid combinedly they are they are trying to meet demand of EV charging station. Third one is during night time. During night time, if you are not having any charging options, sorry, you're not having any storage option in the PV generation side. So we cannot give you any power. It cannot give you any energy. So inverter is zero in this case. So during night time, what you can say is the whole EV charging station demand will be basically fulfilled by your utility grid. So there are three cases. One is favorable atmospheric condition or light load case. At that time, our generation is more, PV generation is more compared to the EV charging station demand, and during that time we can feed the surplus energy to the utility grid. Or second case is unfavorable or overload condition, that you can call as load sharing condition. During this time, combinedly PV inverter and utility grid will meet the demand of EV charging station. And third one is during night time. As we know, during night time there is no energy generation from PV, so wholly the charging station will depend upon the utility grid. Now see here, so using some modulation technique, usually we do whatever control the switching action of the inverter in such a way that, or we use some modulation technique in such a way that we try to get sinusoidal type of output from the inverter, right? And edge charging station, as I mentioned, most of the thing in the charging station are non-linear type. The load are non-linear type. So current, the charging station usually draw the current of this shape. That means non-sinusoidal type. So I whatever current we are generating from PV inverter, that is sinusoidal, and the requirement at the charging station is non-sinusoidal type, then obviously you can say that even during grid feeding condition or even during load sharing condition, whatever current will be whatever current will take from the grid, that will basically non-sinusoidal type, and which is not desirable. So you can see here the quality of grid current is basically decided by the load, decided by the charging station and the load. That means even during grid feeding condition or load sharing condition, every time you will have a non-sinusoidal current that will basically either flow to the grid or either will have to take from the grid, right? So this is a issue. This is a major problem, and we have to mitigate the harmonics. Current harmonic is there in the grid current, and also not only grid current harmonics but also the reactive power. Have also reactive power, right? So in case of non-linear slash you can say that reactive type of load, the grid current would be non-sinusoidal shape and lagging nature with respect to grid voltage. So so this is the major challenge whenever we'll think about the PV based charging station, or and whenever we are whenever we are having a PV DG system and that we are using for charging purpose, charging station purpose, right? You know that whenever we are interconnecting any DG unit, distributed generation system, with utility grid, we have to meet some standard. That means that the grid current harmonics should be less than 5%, as per IEEE 1547. And what we saw here is as EV charging station is mostly non-linear type, and whatever current we are feeding or whatever current we are taking from the grid during different conditions, that is non-sinusoidal type, and its current TSD, the TSD is more than 5%. So we have to do some arrangement so that the current should be less than 5%. Now we are having whether we can use some passive filter or some active filter to compensate the harmonics, right? That options we are having. So this is one option. This is one option. Suppose on the left hand side we have local load, whatever I mentioned, it's basically your suppose EV charging station, right? So because of this, we are the current, whatever current is flowing to the grid or whatever current we are taking from the grid on the different cases, that is non-sinusoidal, and in order to mitigate or in order to compensate the harmonics, grid current harmonics, or even in order to compensate the reactive power, you choose one shunt active power filter at the top common coupling, right? So this is one option. So external active power filter, shunt type active power filter, can be used to mitigate the harmonics, right? Both current harmonics, and also you can compensate the reactive power. But why to use one additional shunt active power filter at the point of common coupling to mitigate this grid current harmonics, or to compensate the reactive power? Already we are having an inverter at this point, right? Whenever inverter already we are using to convert the DC power into AC power, right? To convert DC, whatever power we are generating from PV module to AC form, we are already using an inverter, so there is no need of using an additional shunt active power filter at the point of common coupling. Because if we use an additional shunt active power filter at point of common coupling, basically the cost will also improve, the cost will also increase. That is, we will have high cost, and also we are underutilizing the hardware circuits. Already PV inverter is there, so can we use this PV inverter also for also as an shunt active power filter? That is, if we able to use this PV inverter for both for power conversion purpose and also for compensating the harmonic and reactive power, then there is no need of using an additional shunt active power filter, right? So instead of using additional shunt active power filter, what we can do is we'll integrate the power quality features. So we'll integrate the control technique of the shunt active power filter in the PV inverter itself, so that now this is my system. On the left hand side, PV inverter, and this inverter is having the capability of shunt active power filter. That means we are having the same hardware circuit, one inverter only we are having. That inverter can be used for power flow control purpose, and also the inverter can be used for the compensation of harmonic current as well as compensation of reactive power. So this is single inverter we are going to use, and in this inverter we are going to integrate the feature of shunt active power filter. The control technique of the shunt active power filter will be integrated in this inverter itself, so that now there is no need of using an additional shunt active power filter at point of common coupling. And the advantages is now basically we are effectively utilizing the hardware circuit, right? So, and also in the night time, earlier in the previous case, if you see, during night time this inverter was in ideal state, so there was no power generation from PV module, so there is at that time there was no use of inverter, so it was in ideal state. But with this particular feature, we can, when in the night, even though power generation is zero, but we can use this inverter circuit as a shunt active power filter in the night time. So this particular system or can improve the effective utilization of the hardware circuit, and also it can be used in the night time. The PV inverter can be used in the night time, not for power flow purpose, right? But it can be used for the power quality improvement purpose. It can be used as a shunt active power filter. Now, with this brief idea about the photovoltaic distributed generation based your charging station, let me show you what are the different modes of operation that are possible in this particular system. This is basically my EV. Battery is there, then electric. We are having some motor. Suppose we are these days AC motors are more popular, so I have used one AC motor. Suppose maybe it's PMSM motor, maybe your induction motor, whatever it may be. So suppose it is an AC motor. On the left hand side, you can see that PV module we are having, and also we are having, for more reliable operation, we have connected PV module with utility grid, and this is basically, suppose this is basically a charging station, right? may have complete electric vehicle. I have shown complete electric vehicle, but you can think about suppose you are only used for the charging purpose of the electric vehicle, right? So there are just okay, sorry. There are like as I mentioned earlier, there are you will have different modes of operation, like favorable atmospheric condition. Whenever you are using PV module, that means you have to talk about atmospheric condition also. So so if conditions atmospheric condition are favorable, that means PV will give sufficient amount of energy. So that energy you can use for the charging of the vehicle, and also if it is more than sufficient, then you can supply to the local load, or also you can give the surplus energy to the grid also. The other condition is other mode is basically during unfavorable atmospheric condition. If atmospheric condition is not favorable, in that case, yes, you have to rely on the grid energy. Grid has to supply the power for the charging purpose of the battery, and also to meet the local load demand. And third one is night mode operation. During night time, there is no you are not going to use the energy of PV module. You are not having any option to use the energy of PV module. So majorly we'll use the energy of grid to charge the vehicle, right? And charge the to also will the grid will meet the local load demand. But as I mentioned, at that time we'll use this in the night time. We'll use this inverter, PV inverter, to improve the power quality of the system of the grid. So, in order to develop this system, yes, you'll have to. You can say that first. Yes, you'll have to model it in MATLAB or any software tool for the testing purpose. So first, whenever you are going to develop a charging station, yes, based on that, whatever PV module you are using, same thing, same PV module you can. You'll have to develop in any platform, simulation platform, or software tool, because directly you cannot set up this charging station without testing. So in before developing this type of system practically or physically, basically you have to test it. So you have to think about how many PV modules you required. Then once you model this PV module in any software tool, we have done it in the MATLAB platform. Then only you can say that different controller which are required for the different converters that you can design, right? So this is basically the block diagram. We have done it using two different types of inverter topologies. One is by using two-level inverter-based topology. Same thing. We are having here you can see PV inverter. Then we have used one DC to DC converter. These DC to DC converters are used for extraction of maximum power from PV module. Basically, by properly choosing the duty cycle of the DC to DC converter, we can able to match the load resistance with the source resistance, and by using some I'll show you some conventional algorithm only. So by using some MPPT algorithm, conventional algorithm, you can extract maximum power from the PV module. Then we are having inverter, and this is our grid, and this load is basically my EV charging station, and right. So and on the at the, just below the DC-DC converter, we are having the battery. So this is the local load, and this is basically your charging station, you can say. In that way also we have used. And as I mentioned, we required different controller, like DC to DC converter. We have to use some MPPT controller to extract maximum power from PV module. Then this DC link voltage has to be stable, right? So we have to control this DC link voltage in such a way that the voltage at the input side of the inverter should be maintained at a constant value, right? Then only asymmetric output from the inverter we can get. Then inverter current control. Basically, this inverter current controller are used for basically whenever we we'll have to synchronize this PV inverter with utility grid. So by considering both synchronization part and also by considering the power quality improvement part, whatever that will try to switch the inverter in such a way that it should generate a current based on with, the inverter should generate a current correspond to that reference value. That I'll show you. And also not only two-level inverter, basically as PV based power generation is having its very modular type. At any time, if you want to improve the rating of your charging station, right? Suppose in future demand is more in the charging station, you can easily add some PV module, and based on that, instead of going with two-level inverter, we can have multi-level inverter-based topology, which is very modular type. At any time, if you want to increase the rating of the power rating of your station, yes, easily you can add one more PV module, one more H bridge, and you can interconnect those H bridges, right? That H bridge with already existing H bridge, and with your whole system rating can also be improved, right? And otherwise controllers are same only. So in individual H bridge, whatever controllers we are using, the same controller you can use in each bridge of the multi-level inverter. And the advantage of using or to go for multi-level inverter is yes, we'll have more switching options in these H bridge cascaded multi-level H bridge inverter, right? Cascaded H bridge multi-level inverter. So you can see here with more switching options, whatever output voltage will get, that will be more closer to sinusoidal. So the whatever output we get from such type of inverter, that is whatever output waveform will get, that is more closer to sinusoidal as compared to a conventional two-level inverter, right? So here I have shown some example like this is highly possible that whenever we are feeding each H bridge from different PV modules, so maybe at any instant there will be some shadow in one particular module. So always there is a possibility that each PV module cannot generate equal amount of voltage or equal amount of power. So there will be some mismatch in the power generation of each PV module. So by using some single phase, so some space vector modulation techniques, this mismatch in power or mismatch in the generated voltage from each PV module can also be mitigated, or you can say that I have shown three different cases. One is whenever VDC1 is equal to VDC2. In that case, you can have say 5 different levels of output, that is -2 VDC, minus VDC, 0 VDC, and 2 VDC. But whenever there will be a mismatch, means if VDC1 is greater than VDC2, right? So at that time, the levels will also be more, right? And but under one particular condition, that is if we have to use appropriate modulation technique, right? So we have to control the inverter, multi inverter in such a way that even though there will be change in voltage of H bridge, we have to control the switching action in such a way that with even though there is change in voltage, the levels will be more. You can see here, if VDC1 is greater than VDC2, you can get around 7 levels of output voltage. So if the ratio between VDC1 and VDC2 is 1:2, then you can get 7 level. If the ratio between VDC1 and VDC2 is 1:3, then you can even get 9 levels of output. So this multi-layer inverter is very modular structure. Just a minute. Just a minute. Just a minute. Okay. So just a minute. Sorry. Okay. Okay. So I was here. So this is the case, and let me show you some different voltage level of each HV cell. We can have different. Let me show you in pictorial form also only. So whenever VDC1 is equal to VDC2, you can get 5 different levels, right? And this yes, we have to control the switching. Now it's not possible to go in the detail because of time limits. Otherwise, I could have explained it. Basically, based on different levels or the voltage ratio between VDC1 and VDC2, have to go for the switch. VDC1 is equal to VDC2, we can have 5 levels of output. If the ratio between VDC1 and VDC2 is 1:2, then you will have 7 levels of output. If it is 1:3, you can have 9 levels of output. So with this, you can say that we are getting output from the inverter that is more closer to sinusoidal, which you cannot get by using simple 2-level inverter, right? So that's why in if multi-layer inverter is convenient to use for such type of application, PV application. So that at any instant you can add one particular PV module, and as the CHB MLI based inverter topology more is modular type, even with increasing inverter increasing different, you can also get a better shape of output, right? So I'm not going into this part. So as you know, whenever you are going to implement it, so first one is whenever you're going to implement it in the MATLAB or some any platform, first you have to model the PV module, right? And the challenges in modeling of PV module is all parameters basically we don't get from the data sheet, and some parameters are missing like series resistance, shunt resistance, all these things are missing. These basically 5 parameters are basically not available in the data sheet of the PV module. So first thing in the modeling of modeling of PV module is basically you have to estimate those unknown parameters by using some any technique. Like here we have used Gauss-Seidel technique, and basically if you go through some literature, so these are some basic equations, conventional equation that you can use, and if you solve these equations by using some Gauss-Seidel or Newton-Raphson method, you can estimate those unknown parameters of PV modules. So once you'll have all these parameters, that means both known and unknown parameters, you can easily model the PV modules. Here in this case, in our system, we have used one PV module of Maharshi Solar. So here the available parameter was like this, and we estimated the parameter, and by using all these known and unknown parameters, or known and estimated parameter, we basically model the PV module, and we exactly got the result. Whatever we are getting practically, the same thing we got in the MATLAB also, right? So these are the different characteristics, and actually the one PV module rating was 128 watt. So the same thing. Actually, we got whatever the manufacturer was claiming, the same thing we got whenever we model this PV module, right? And I'm not going into it. And finally, as per the charging station requirement, you can connect number of PV module in series and parallel. So we first we have designed a 2 kilowatt PV system, PV charging station system, by connecting 4 number of module in series and 4 number of modules in parallel, right? Similarly, for multi-line inverter, we have used 3 number of modules in series and parallel, right? Then, as I mentioned, we can use some MPPT algorithm technique to extract maximum power from PV module. For this, you will have to use DC to DC converter, and here you can see by varying this duty cycle D, you can make load resistance with source resistance value, and as per maximum power theorem, you can extract maximum power from the PV module. And what exactly this algorithm is in our system, we have used perturbation observe method. Continuously we were sensing the present voltage and present current of the PV module, and also we are keeping the track of previous sample data, right? And by using the present sample, basically you can see that we basically compare the present sample of power with previous sample, and if present sample power is more than previous sample power, we basically try to move in this forward direction. And one particular point, whenever you can see here, after this point, the present power will be basically less than future power. Sorry, present power is less than previous power. In that case, you can say that you have reached the maximum power point, and after that, it will oscillate around that MPP. Right? So this is a conventional type perturbation observe method which we use. And based on the conventional techniques, we design the inductor and capacitor of the DC to DC converter, and that we use. So first part is over, PV module. Then we used one DC to DC converter for extraction of maximum power. Then for the charging station, we also use one bidirectional converter. So what we can do is, what is the role of this charging station is, suppose this is our battery, this is the battery, or what is the need of bidirectional converter is when during motoring condition, basically we boost up the voltage and we use this converter as a boost converter. And as per the our requirement of the, or voltage requirement of the motor, right? Basically we boost up the voltage, and whenever during dynamic braking condition, whenever that means whenever your vehicle is moving in the downhill direction, or whenever deceleration is occurring, at that time basically your whatever motor you are using, it feedback energy to the battery. So these are the requirement of DC to DC converter, inverter, and bidirectional converter in our system, or whenever you are planning to develop such type of charging station. And next is here I would like to, as I mentioned, the power quality issue. As I mentioned, in the PV inverter, basically we integrate the control technique of shunt active power filter, right? So that instead of using a separate inverter, the same PV inverter can be used for power quality, so grid current compensation technique, grid current compensation purpose, harmonic current compensation purpose, and also for reactive compensation purpose, right? So what we did is basically continuously we are trying to sense the load current, or whatever the current demand of the charging station, right? Here we have considered as a nonlinear load only. So we were sensing the VPCC voltage, point of common coupling voltage, and the current, load current, you can say. And by sensing the voltage and current, we continuously we were trying to find out the active power and reactive power demand of the charging station. And from that active power and reactive power demand of the charging station, like this P and Q, we can say, we try to find out the non-linear, or the harmonic component of current, right? Harmonic and reactive component of current. That basically, here you can see that IC alpha and IC beta. So combinedly, the direct axis, because now we have developed the single phase system. So the alpha quantity, that means only single phase quantity we have taken, and whatever load harmonic current are there, right? Whatever harmonic component of current is required by the load, we have considered only that part. That means, respond to this harmonic current requirement of the load, we are basically trying to find out a compensating current, right? Similarly, here you can see E. This is basically harmonic power requirement of the load. Second one is DC power requirement or non-fundamental power requirement of the load. The third one is reactive power requirement of the load, right? So considering all these things, we basically try to find out the compensating current, and like this you can say we are sensing VG or VPCC, and we are sensing the IL load current. This is the current requirement of the your charging station, and by using all this quantity we are trying to find a compensating current value which is required to generate from the PV inverter. So if your PV inverter will able to generate all the non-sinusoidal requirement of the load or of the charging station, then you can say that uh, all the harmonic and reactive component demand of the load, if PV inverter will supply, PV module will supply, then the rest of the current, whatever current is going to the inverter, to the grid, or whatever current we are taking from the grid, that will basically pure sinusoidal type. So with this, let me show you some result. This is a block diagram of single phase grid connected PV system under suppose light load condition. So here we can see that suppose our load demand, charging station demand is 765 watt, and as our PV module is generating around 2 kilowatt of power, so battery is taking whatever power it requires, that means 320.2 watt, and the remaining power we are able to supply to the grid, right? Similarly, reactive power, if you say, if the charging station reactive power demand is 187 bar, and then inverter is generating that much reactive power demand of the charging station or the load, and hence you can say that almost 2 to 3 bar. So we are also able to get the reactive power of the grid, right? We are not taking much reactive power from the grid, and thereby you can say that the voltage and current at the point of common coupling will be pure sine, means almost in phase with each other. And also here you can see the load current FFT analysis, then the grid current FFT analysis. So grid current FFT TSD, you can see it is below 5%. Even though the load is drawing a very non-sinusoidal type of current, like this here you can see, but grid current is almost sinusoidal. Grid current is almost sinusoidal with very the TSD less than 5%. So on the different cases, but for both 2-level and multi-level inverter cases, we have simulated and got the desired result, basically you can say. And as I mentioned earlier, under different conditions, like here you can see during atmospheric bearing condition, when suppose at 0.4 second we are changing the irradiation from 1000 to 600 watt per meter square. Accordingly basically is also supplying some power, or in both way we have done both PV both for 2-level inverter case and multi-level inverter case. For both cases we did it, and as I discussed, we got desired results, right? So just let me show you one result only. Reactive power compensation also. Here you can see that during night time, maybe. Here you can see that here we have given the name of that controller is power quality enhancement controller. So here you can see that till this point 0.02 second we have turned off the power quality enhancement controller. That means we have turned off the PV inverter, whatever control we are doing for the power quality enhancement. Sorry, am I audible?
Now it was now it is okay, sir. Earlier there was some glitch.
Yes, yes. Here I would like to conclude here with this particular result. Here you can see that whenever we are turning off the power quality enhancement controller, the load current was non-sinusoidal, and hence the grid current was also non-sinusoidal. That means PV inverter was not able to compensate the harmonic current as well as reactive power. The moment we turn on our controller, power quality enhancement controller, you can say. So now the PV inverter started to supply the harmonic current demand of the load and also reactive power demand of the load, and by that it is forcefully making the grid current sinusoidal. So till 0.02 second grid current was non-sinusoidal. The moment we turn on this power quality enhancement control, it becomes sinusoidal. From this also you can see, right? And also in phase with utility grid. So also in the night time, as I mentioned, we are only we use the PV inverter only for power quality enhancement purpose. That means in order to mitigate the harmonics, grid current harmonics and reactive power, we use this PV inverter. So and the active power demand is basically supplied by the utility grid. Here you can see the utility grid is supplying the whole active power demand, right? The local load demand as well as the battery charging demand. So during daytime, PV was supplying power, but during night time, PV power was zero. So all the requirement of the battery and grid and the load was basically being supplied from the grid. So we made some comparison, and here I would like to conclude. So we basically discussed in today's talk. We discussed about first we discussed about the need of EV and the hurdles or infrastructural hurdles we are having at this moment to switch from IC engine based vehicle to electric vehicle. And in order to create that charging station, what are the power quality problem we can face, that we discussed. And in order to mitigate or in order to resolve these power quality issues, how can we use the same inverter? Even though I didn't go in detail about the control part, but yes, you might have got an idea, because if the major thing is we can use the control technique, whatever may be the conventional control technique of shunt power filter, that control you can use or you can incorporate in the PWM control technique of the PV inverter itself. So by using those techniques, we can say that not only power flow control, but power quality can also be improved by the PV inverter itself. So with this, I'd like to stop here. So if anyone is having any query or anything you want to ask, please you can ask. Any question?
Participants, any queries? You can please ask, sir. Sir, can they contact you like for any like future roles and for any queries if they have in this working in this area?
Yes, yes. They are free to contact me. If anyone is working in this area, then yes, they can contact me. They can get get my email ID, phone number from our
Oh.
institute website also, right?
Okay,
So,
okay, sir.
yeah.
Yeah, any queries? Okay, sir. Then I think they are fine with this thing. I think they are clear with all whatever you have discussed.
Okay, okay. Fine. Later also they can
Oh,
through mail
okay.
also you can discuss, not an issue.
Thank you, sir, for an informative session. You have covered a lot of things, right from explaining us about the need to move to EVs for mobility, its economics, battery charging, density improvement, different types of EV chargers, power quality issues. You are given a clear idea of grid-tied PV interconnected systems, multi-level inverters. Actually, many more things, like beyond the thing which I can talk about. A lot of information you have shared with us. And this really is going to help the resident students who are working in this area, and they will be greatly benefited with it. Thank you, sir, for joining with us, even if your busy schedule. Thank you so much.
Thank you for giving me the opportunity also. Thank you for the